I want to start by just kind of going over a few logistics and I guess um, background for our meeting the next couple of days. But I wanted to start out by thanking all of you for joining. It's nice to see so many folks online and to see such engagement in what's been a pretty difficult year for many of us, and Zoom fatigue is real. So I'm hoping that the quality of the presentations over the next couple of days is enough to keep you engaged and excited about the meeting and the work that we're doing. So for the next 3 days, we've got kind of a suite of talks lined up with some background on where we've been for the last year today, and then also I look forward to some exciting new activities that folks will be sharing with us. So as we're getting started, Elizabeth had this up as folks were logging on, but just keep in mind the kind of expectations for the meeting, that we'll have constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. And towards that end, I think our conversation will be a lot more effective if we can raise hands. So it depends on what version of Zoom you're using, but at least on mine, it's moved. So raising hands is under the reactions. And you can also, give a thumbs up or a clap. Use the chat then also. I think it'll really help for the number of people that we have online, and just kind of it helps me a lot to kind of gauge engagement if folks are using the chat. Presenters only get 12 minutes, which is a little bit shorter than usual, but I'd like to keep to that time rule just so that we can have time for some brief discussions after folks' presentations, and then also to allow for the transition between speakers. I think that's critical, kind of given the format that we're in. And then lastly, we'll have a virtual coffee break both tomorrow and on Wednesday. And if you've updated to Zoom, you'll be able to choose what breakout room you go into. So you can, it's not quite like being at the Mesa Lab and getting to have nice treats, but you can at least choose who you're going to go talk to, and you can find that person who you've been wanting to touch base with for the last year that we've been sitting in our basements or in our home offices. Do folks have questions or comments before I launch in on the land model updates?
Looks good. We're all clear.
Cool. Sounds good. Yes, I should say Jackie Schumann is going to be moderating the chat. I at least have a really hard time with presentation mode and being able to watch the chat and give a presentation and kind of keep track of things. So for the next few days, we'll have one of us from the working group leading the discussion, and then somebody else helping to moderate the chat. So Jackie's doing that today. Thank you. So to start the meeting, I'd like to kind of acknowledge Drew's contributions. I guess 4 years out now. So since 2018, we've been giving an award for the best graduate student and postdoc presentations at the meeting. And this is really to remember kind of Drew, who is a friend of many of us in the working group, and had a pretty uncanny knack for both doing great science and taking big spills like here skiing. But really his contributions to the working group are still being felt, and we'd like to acknowledge really great presentations from young scientists that'll be presenting. And so there's a number of folks that are qualifying, or that fall into this postdoc and grad student category. So just a shout out to Drew and encouragement for folks to continue doing really excellent work as Drew did. So last year we had 2 winners of the Slater Award. So Leah Birch was formerly at Woods Hole, gave a really great presentation, and her work has been a pretty big contribution to the developments of CTSM 5.1 that I'll talk about today. And then Jessie Needham will be presenting, I think, tomorrow. But she also gave a great talk last year on some of the work that she's been doing with Fates. So congratulations to Leah and Jessie, and we look forward to hearing from more great presentations moving forward. Kind of looking back at the last year, I realized that a lot has happened in the 11 months that we've been in quarantine, but I wanted to Acknowledge that Dave Lawrence won the CESM Distinguished Achievement Award last June, and Daniel Kennedy won the CESM Graduate Student Award. So it's been, it was a nice recognition of the work that members of the working group have been doing. And if you weren't at the meeting in June, I just wanted to give a shout out to Dave and Daniel for their awesome accomplishments. So for the last year, really, we've been, it's been kind of a rough road, I would say, for many of us, but I think we've still continued to do some pretty incredible model developments. And so I'd like to spend the next half an hour or so talking about some of those developments, giving a brief overview of some of the community projects that are ongoing, and then give a brief introduction to some of the upcoming work, kind of realizing that a lot of the upcoming work will be covered in presentations over the next few days. And so what I have is just kind of a short list of upcoming work that at least we know of here at NCAR. And if your project isn't on that list and it needs to be, we can talk about how that can happen. And so I guess to start out, really before going too far, I want to acknowledge a lot of the work that the software engineering group has done in getting CTSM 5.1 up and ready to go. So this is just a screenshot from our call last week. And so Bill Sachs, Greg Lemieux, Ryan Knox, Eric Kluzek, Negan Shabani, Suniva Indras, and Sam Levis have been really critical to the success of CTSM and getting this next version of the model up and off the ground. And in particular, I wanted to give a shout out to some work that Sam and Bill mostly have been doing to perform grid cell level Waterbeck challenges that are bracketing the entire run loop. So this kind of is an old issue that we needed for debugging and testing. And so while it's not quite as, the magnitude of the accomplishment might not be quite as great as the level of the NASA team that was working on the launch and landing of Perseverance, I think the maturity of the CESM software engineering team is really just as high as the individuals that we got to celebrate last week with this landing. And so I wanted to give a shout out to the software engineers, because often we don't celebrate their work enough. So like I said, CTSM 5.1 is nearly ready for game time. We made that tag, I don't know, 6 months ago or so, and have been adding quite a bit to it. This is the short list of what's on there. And so there's a lot of new science that we've included in CTSM 5.1. And I wanted to highlight a few of those. So one of those is biomass heat storage, which was a contribution that Sean Swenson had made. He presented on this at the working group meeting maybe a year or two ago, but that's been incorporated into the main branch of CTSM. Another one is Leah Birch's changes to Arctic and boreal phenology and allocation, which also came with some bug fixes to the Luna model. We'll hear quite a few talks from Yichi Luo's group using the matrix approach, and so CN matrix is part of or nearly part of CTSM 5.1. And then I think excitingly, fates and some reduced complexity model of fates are nearly up to main. And most notably, we've kind of pulled the fates development so that fates is on the main branch of CTSM, which I think moving forward will help the development of fates and the development of CTSM kind of stay harmonized in the upcoming months and years. Included with that is some things that we talked about at the CESM workshop last June, which includes some reduced complexity modes like fates SP and no competition modes that Rosie and others have been working on. Lastly, there's also been a release of WRF CTSM. This is a beta release that Dave will talk more about in terms of using CTSM as the land model for weather forecasting. Oops. So kind of just to give a quick overview of what some of these code changes look like. So this is again from Leah's work with the Luna bugs and phenology. And this is just survival probability. So survival probability for a whole bunch of PFTs in Whittaker space, so over temperature and precip domains. And there's a lot going on here, but what I want you to take away is that in CLM 5.0, there's a lot of purple, which are dead PFTs. And the problem with dead PFTs is once they're dead during spin up, they never come back. And so what Leah's changes did was improve the survival, especially for Arctic and boreal trees. So we've got better survival in CTSM 5.1 than we did in CLM 5. So that's kind of the motivation for some of Leah's work, and then the phenology changes also change aspects of the seasonal cycle of carbon cycling at high latitudes. Another one of the highlights that I wanted to bring up was the changes from biomass heat storage. So this is just a plot of what we're calling, this is basically what CTSM 5.1 will look like. This is kind of a beta version of CTSM 5.1 that has Leah's phenology changes into it. And the take-home message is that the model is cooler with this biomass heat storage, nearly a degree in some places compared to where we were before, and especially at high latitudes. So another feature of the model that is pretty untested, I would say at this point, this plot is less than a week old, is that with this addition of biomass heat storage, 2-meter air temperatures are cooler with the model. So we've shown these kind of ILAM plots for a number of years, and typically the colors go from red to green as you go from left to right on these plots. And we're going the other way for a certain extent now, so that's good. It means we have some work to do in future versions of the model. But what I'm showing here is ILAM scores for CLM 5 with the phenology changes, and then CTSM 5.1, which has the phenology, biomass heat storage, and everything else on that list that I just showed you. And the biggest thing is this decline in leaf area index, which is I would say a new feature of the model, and especially so what we have higher leaf area index in the model, and this might be expected given the Luna bug fixes that Leah's changes brought in. And I have a shout out to Keith here because Keith has done a ton of work running. I cut this plot down a lot. We've done a lot of simulations as in the testing of CTSM 5.1, and Keith has really been the one who's as always kind of keeps us on track and everything organized. And so I wanted to just kind of show what this looks like. These are the bias plots for leaf area index, I think, compared to AVHRR. And so we already had a high bias at high latitudes in CLM 5, and that bias has gotten worse, especially in the mid latitudes with CTSM 5.1. So this is one of the things that we'll be looking at kind of moving forward is ways to improve the biases in the model, to improve our ILM scores and to better match observations moving forward. And so just to give an overview of what the kind of planned development is, and I put up here just the CLM, just the land model working group development kind of trajectory in blue, and then the larger CESM development that's happening in green. And so we're kind of in this middle of the plot where CTSM 5.1 is pretty much done with phenology, biomass heat storage, fates, and the matrix. All of this is on a branch that we're calling the parameter perturbation experiment, or parameter perturbation ensemble. So Dave will talk about that a little bit more in his talk. This is basically, though, to start with, a one at a time parameter perturbation ensemble that we'll be doing with the number of parameters that we've pulled out of the model, and then eventually using those to recalibrate and evaluate the model moving forward. So this branch will be kind of a long-lived branch that we'll be working on for a long time, with the idea that after doing this parameter perturbation ensemble, the revised parameter values that we come up with will be plugged back into the model in a future tag. So now that this PPE tag is nearly finalized, There's one more tag that needs to come in for the coupled model, which is a revision to the dust fluxes that CLM passes to CAM that Langley and Natalie Mahawald have been working on at Cornell. And those will, so CTSM 5.1 and these revised dust fluxes then will be put into a CESM 2.3 tag, which will be used for die-core evaluation. So one of the large activities for CESM is both testing different die cores, atmospheric die cores to do variable resolution grids. So on the atmosphere side, that's a major kind of activity within CESM, and then also the ocean model switching from POP to MOM, and so that's also ongoing. So these two, an atmospheric and an ocean, large changes to the atmosphere and ocean model are happening in the next year for CESM 3. And our plan moving forward is that when those, when CESM needs a new tag, that we'll just be pulling from the main development branch of CTSM going forward. So for timing, that's, hopefully that CESM 2.3 tag gets done summer or maybe early fall, so that they can really get going on the testing of the die core. So in advance of that, I think we need to do some testing on the land model working group side. This is just a suggested list of simulations that we could run, and it's probably worth coming back to this as a working group to talk about what we do or don't need. Given the changes on 2-meter air temperature from the biomass heat storage, it's worth running this in running CTSM 5.1 in coupled mode. That's something we haven't done yet, just to see how that changes land atmosphere interactions. So what I'm suggesting here is that we run some F2000 cases, which are just KM CTSM with the slab ocean cases for the year 2000, with the SP and BGC versions of CTSM. I think we also need to kind of repeat this normal spin up and testing that we do with the GSWP3 forcing. It's just a clean simulation. And then increasingly, we're using this CRU JRA forcing. This is the forcing that's used for trendy simulations, but we're also using it for other experiments. SMILE is one that I'll talk about in a little bit. And there are differences between GSWP3 and CRU JRA. One advantage of CRU JRA is that it's being updated every year, whereas there's no plans, at least that I know of, to update GSWP3 forcing dataset. It stops in 2014, and that's about as far as it's going to go. So besides, these kind of baseline tests for, where we were with CLM5, where we are with CTSM 5.1, now we also have the opportunity to start running some FATES simulations. So these reduced complexity modes, in particular FATES SP and FATES NoComp, to start learning about what are differences between FATES and the big leaf CTSM version of the model. And at least for now, I don't know if it's worth running those with CRU and GSWP3, but for sure we need to run them with GSWP3, and then also a coupled model as a smoke test to make sure that fluxes are getting passed back and forth between CTSM FATES and CAM. And then the other set of experiments that I think that we've already run some of are these Plummer 2 sites. So Sean Swenson and Keith Olson came up with a pretty slick workflow to run 170 tower sites, kind of almost push button, so that those simulations have been done for CLM5 SP, and I think we should repeat them again with CTSM 5.1. And there's potentially value of repeating those with FATES, or at least a subset of the sites with FATES, with some of the reduced complexity modes of FATES, to start learning about differences between the models. So I'd like to switch gears a little bit and talk about some of the community projects that are out there. And this is kind of an overwhelming list when I put it together. It's like, oh my gosh, there's a lot of things going on. And so I'll run through a few of these and then provide a little bit more detail in the next couple of slides. And so a year ago, we talked about running the CESM SSP extensions out to 2300. And so those have been done. There's a simulation with SSP 126, the SSP 534 overshoot, and the SSP 585. All of those are published on Earth System Grid, and Charlie will talk about some of those results in his talk later on today. The other set of community experiments that the Land Model Working Group contributed to last year were these SSP-RCP combinations that Peter Lawrence did. And so there's 3 ensemble members of SSP-126 run with the 370 land use and vice versa. So 6 ensemble members altogether, complementing the straight versions of those, the SSP-126 with 126 land use change. Those simulations also are done, and I think they should be published on our system grid, although I haven't checked that recently. Next is the CESM2 large ensemble, and Gokhan and Clara are the contacts here for that. That's a 100-member ensemble that goes from 1850 to 2100 using SSP 370. And interestingly, they've saved a ton of daily output, which is really interesting to look at. And I'll talk a little bit about some of the ideas that we have for using that project. Another ensemble, if you need more ensembles, is the CESM2 CMIP5 ensemble. So this is a set of 11 CESM2 simulations that's forced with the CMIP5 RCP 8.5 forcings out through 2100. And so Marika Holland and Cecile Hannay are the 2 contacts there. They're kind of actively looking for people who are interested in comparing the CESM1 large ensemble, which has CMIP5 forcings, the CESM2 ensemble, which also has CMIP5 forcings, and then the CESM2 large ensemble. And so with those 3 sets of ensembles, you can start comparing differences in the model structure versus the forcing uncertainty in some kind of interesting ways.
Hey, Will?
Yep.
We have a question.
Oh, good.
You want to take a question now? It's in the chat.
Sure.
Do you want me to read it?
Yeah, can you read it? I don't see the chat right now.
Sure. Alan Robach asks, does the daily output include correct max and min temperatures, or do they include the bug that they are the same? I didn't know.
I have no idea. I haven't looked, Alan.
Pretty sure they corrected it. I'm pretty sure it's correct.
Okay, and then Isla just put into the chat that the daily max and min are corrected. The bug is not there.
Great.
Thank you
Thanks
for that question.
The next set of ensembles that TSS is helping contribute to are both SMILE and the S2S simulations. And so those are being conducted by the new Earth System Prediction Working Group led by Steve Yeager and Jager Richter. So the S2S simulations have already been done, and SMILE is just getting kicked off now. And SMILE is a set of ensembles using their kind of initialized hindcasts, I think is what Steve's calling them, but they're 2-year simulations that are being kicked off kind of quarterly, so 3 to 4 times a year. And I think there's 10 ensemble members for each of these. And those are with initial conditions provided by CLM. Donica ran these initial conditions. So they're CLM5 forced with the crew JRA forcing. That's the initial conditions that are going to get plugged into the SMILE simulations. Donica has made the CLM5 trendy simulations available on Earth System Grid. So those will be used for the Global Carbon Cycle project. Keith has published the Plumber 2 experiments, and again, that's for 170 flex tower sites using some gap-filled meteorology and part of the Plumber protocol. Keith's also participating in the Urban Plumber experiment. I haven't heard an update on that to know exactly what the status of those simulations are. And then the last kind of two new community projects that'll be upcoming are the parameter perturbation experiment that Dave Lawrence is leading up, and you'll hear from in the next talk. And then this fire community experiment is being led by Simone Tilms. And so those will be fully coupled historical runs using CAM6 and CTSM 5.1, looking at historical fire emissions and looking at the interactive role of fire during the 20th century climate, looking at 20th century climate trends. Notably, we're using CTSM 5.1 for this because there's been an update to the fire code, and so that'll be important for these fire simulations that Simone's running. So a lot going on. I think I showed this plot at the summer meeting, and so this is just two of the CESM2 extensions out to 2300 that Charlie will be sharing. There's another one that's been run, so the SSP 126 has been run too, and there's some interesting patterns to start looking at that we'll hear from Charlie about. But I wanted to give these simulations a plug because we have the CESM 1.2 extensions out to 2300 that are available, and now these new CESM2 extensions. And as far as I know, the CESM2 extensions are kind of an underused resource. So if folks are interested in looking at these, like I said, they've been published under a system grid. For the CESM2 large ensemble, we just had a meeting last week with collaborators in Korea and really all over the world. And my take home from that is that I think as a working group, we could do a better job engaging with the large ensemble community. And that's a challenge for a lot of reasons. One is just the data volumes. I've had a hard time making notebooks that don't crash when you're reading in, 250 years of daily data. But there's a number of projects that have at least been started. And so Daniel has a really nice, some nice work looking at water and carbon cycle variability in the CESM2 lens. Jackie and I have been talking about fire risk and calculating fire risk in different regions and in different ways. I've started looking at water use efficiency and trends in water use efficiency with this simulation, and then also at what I'm calling extended summer. And I wish I could show plots for this, but at least right now we're still not allowed to show plots from CESM2 large ensemble work. But this extended summer is looking at kind of patterns of snowmelt and the length of the growing season, especially at high latitudes. Gordon and Keith Rogers have been looking at initial conditions and seeing how differences in the initial conditions from the CESM2 lens might add some predictability to the system. And then Donica has been thinking about variability in food production. So a lot of, and these are really just kind of very preliminary studies at this point. The timeline for the CESM2 large ensemble is that the overview paper will be hopefully submitted in April and accepted by June. And at that point, they're looking for kind of some early release papers to be published on that June timeline. And after that, the data will be made available more broadly. And it'll be kind of open season on large ensemble. So, but like I said, a ton of really great data to look at there.
Hey, Will.
Yep.
Before you move forward,
Sure.
Keith Olson has an update in the chat about Urban Plumber.
Ah, good.
And so phase 1 has one site completed, and then phase 2 will have 20 urban sites completed.
Great. Thanks, Keith. I like this format as opposed to being in the seminar room. You guys can just jump in and tell me when I've got stuff wrong. Yeah, so going back to this kind of upcoming work, the next work, like I said, we're nearly done with the PPE tag, this parameter perturbation ensemble tag. And when that tag's done, that's what we're calling, that's the end of CTS, or that's when we'll call CTSM 5.1 being complete, and we'll start working on CTSM 5.2. with the addition of these dust fluxes. So again, the dust fluxes will be coming in before we make the CESM 2.3 tag for the DICOR evaluation. And then we're defining CTSM 5.2 as contributions to the model that require new data sets. So I'll go over what some of those are. And then there's a lot more that's coming in. So these are just kind of new and ongoing features and developments that people are contributing to the model. So the first of those are Mesoroute that Naoki's doing, reservoir operations from INE that we'll hear about, and then the representative hill slope model from Sean Swenson. There's also terrestrial DOM fluxes, ozone impacts on JMEX, and then the Mimics soil model. And I wanted to just kind of give a shout out here to the Norwegian group has been very active and participating in GitHub, and so that's why all of these are up here. So thank you to those of you who have upcoming work that you'll be submitting pull requests for. It's nice to have a heads up about what that is ahead of time. And then some of the other new work that we already have, but that we need data sets for to run in the model, or the shifting cultivation work that Peter Lawrence has done and that Donica's run as part of Trendy. So a bunch of new stuff coming up. The representative hill slope work that Sean has done, he showed this, I think, last year at the Land Model Working Group. This is just looking at north and south facing slopes and the incoming solar radiation averaged over the year that you get. So kind of appropriately, slope and aspect controls how much incoming solar radiation you're getting. And some of the new work that Sean's doing that hopefully he'll be able to present at the next working group meeting is on some of this precipitation downscaling. And so in the hill slope model, he's got kind of lowland columns and upland columns, and then is scaling the precipitation so that you get more precipitation, and more of that precipitation falling as snow in the upland columns, whereas you get more rain in the lowland columns. So pretty exciting new features with the hill slope model that we'll be able to start exploring both on the big leaf CLM side and then also using Fates. And then the last kind of new development that's going to be coming online is an effort that's supported by 3 different directorates at NSF. So the Cyber Infrastructure Directorate, Bio and Geo Directorates, which is stimulating neon flux tower sites. And this work is kind of moving along fairly quickly. The idea here is to take neon metadata and then run CLM in a containerized modeling system, and then have tools for analysis. And this kind of on the NCAR side, this containerized modeling system and tools for analysis fall into activities that are ongoing with CESM Lab. So CESM Lab is a containerized version of CESM that includes right now CLM5. So it's run in Docker, or it's available through Docker, and it has the CESM Lab part is that it has a Jupyter Lab notebook kind of capability built into it, and it lets you run CESM, and in this case, single point versions of CLM offline. You can do them on your computer, you can run them on the cloud, you can run them on a cluster, and you don't have to port all of CESM to your local machine. So I think it'll offer some exciting opportunities to engage ecologists and also for training some new things. So Donica, Gordon, and I on the NCAR side will be kind of rolling out more of that, along with Jim Edwards and Brian Dobbins, that have been contributing quite a bit. And then lastly, I wanted to kind of just give a shout out to the newsletter. And so it's hard, especially when we don't get to see each other, to stay connected to what's going on. But so Dave and Donica and I have started publishing this newsletter. Hopefully it'll come out 2 to 3 times a year. And it's a nice way to get a summary of some of the updates that are going on aside from these meetings. If you want more information, GitHub is always a great source for this. And then lastly, the CESM workshops and working group meetings. I think the June meeting is also planned to be virtual. And then after that, hopefully we can return to seeing each other again and drinking not so great coffee and big brownies. So I think timing wise, I'm a minute over. And so we have a little bit of time for discussion after Dave's talk, but maybe in the interest of time, I'll stop sharing. And then Dave, if you want to give your presentation, then we can have a discussion as a larger group.
Okay. That's not my talk. This is my talk. Okay. I'm going to talk about two things today, an update on CTSM and also the PP, like Will mentioned, and there's a whole host of people involved. Obviously, can't even list them all here. But thanks to everyone who's been contributing to these big projects. So there we go. Okay, so CTSM, you've been hearing about this for a while now, and this is the effort at NCAR to unify CLM and NOAA-MP to build this unified model for research and prediction in climate, weather, water, and ecosystems. So I've gone through the rationale several times before, but the main idea is to streamline our development process, and so that we're getting the advantages coming from both the weather and the climate and ecosystem hydrology communities are all building towards the same modeling framework we use. And so today I want to report on the coupling to WRF that I mentioned. It's been released to the community in September 2020, and it's quite easy to use. We have a good user's guide that describes all the steps. Both myself and Fei Chen, two senior scientists, have successfully completed the steps. So I do feel like that you can say it's a true statement that it's possible to run this. We're coupling through the Lilac architecture. This was work done by Nagin Sabani, Bill Sachs, Sam Levis, Mariana Vertenstein, principally, and others. And so that's available now. And we've been looking at a few simulations just to sort of evaluate how it's looking. And obviously we know this model works well for climate applications, so we don't need to evaluate that. It started with CLM. So the question is whether or not it's working well in higher resolution simulations. So these are 4 simulations that we've done to compare WRF, NOAA-MP, WRF with CTSM5 with what we call the NWP configuration, which is our fast configuration with fewer PFTs for grid cell, turning off plant hydraulic stress and a couple other things to make the model run faster. And then the more climate configuration with full subgrade heterogeneity, what we call WRF CTSM5 CLMSP. So this is just showing 1 month. In July 2013, these spectrally nudged runs, so that the larger scale climate is being constrained. So it should be relatively close to observations. And what you can see here is that first, CTSM performs as well or better. And to be fair, I cherry picked this a little bit, but you'll see in the next slide, it's fairly robust that the improvement exists, that, comparing NOAA to NOAA-MP, which is performing not as well, especially in the central US, CTSM5 and then CLMSP is showing the best performance. And this is encouraging. I wouldn't take it as being too meaningful because obviously there's a lot of variability across years and sites and whatever, we know that. But it's encouraging that it's not a lot worse, I'd say that's for sure. And then if we just look at across months, each one of these is a month. We've run the simulation for 1 year at this 27-kilometer resolution and looking at the RMSE for daily Tmax. And what you see, the black line is the CTSM5 CLM-SP with that full heterogeneity, surface heterogeneity. And then what you see is in pretty much all months, that is the best performing simulation. So that's, again, encouraging news that it's not just 1 month, it's occurring throughout the year. This is just showing the Tmin. So the Tmin is also showing similar trends, if you say, in terms of the performance. So that's the good news. The bad news is that CTSM5 NWP configuration is a little bit slower than WRF NOAA-MP, but that's okay. But CTSM5 with CLMSP is about 40% slower than WRF NOAA-MP. So it's a big cost. And this is preliminary numbers, and we have to go back and evaluate that. But that's one big reason why people would not typically run with this full subgrid heterogeneity. So I do think we want to come back to that and see if we can whittle that down a bit. The other big activity in terms of CTSM that we're working on related to WRF applications is trying to refactor the code that generates surface data sets, the tool chain. And what we're trying to do is take what was a relatively complex process that was hard to do, and we rarely wanted to do it, and users could never really figure it out, to something where it's very easy to use and run. And the main motivation here is that every WRF user runs their own domain. So you need to make this easy. Otherwise, people are not going to take up using CTSM. And so through the work of Negin Sabani and Ms. Sam Levis, they have put together this set of tasks. I'm not going to go through the details here. But a couple of salient points are that it's now just 2 clear steps to create the surface data set. And one really nice feature is that the option to stop at making the name list, the mapping files of the surface data set. And so particularly with a name list, you can stop after creating the default name list, and then you can go in and modify if you have different raw data sets you want to use. Say you have a higher resolution version for the US that you want to use rather than our global version for the plant distribution or soils or whatever, you can go in and modify that very straightforwardly. And then the other really nice feature is that you don't need to know a lot about mapping files and other nameless aspects in the land use text file. Things that people have tripped up people in the past, you essentially don't need to know this information anymore. It's handling it all under the hood. So that is going to be a really nice feature. It's almost done. And so the next steps are, and not necessarily in order, are to keep working on physics development. See Will's talk. What we're really recognizing is what we need now is an overview paper, so that people know what they're referring to, especially from the weather community. People don't want to switch over to use WRF CTSM if they don't know how its performance is. We're going to finalize the surface data set creation. A feature, if we want to use a regional WRF model to do BGC type simulations, is we need a good method for initialization of the BGC. And so Sam Levis and I and Bill Sachs are going to work on that to try to come up with an efficient way to initialize the BGC. And then really for the weather community to get involved, they need to have a high resolution version and test it in forecast mode, which we haven't done yet. So that's a big thing. Refactoring the hydrology, continuing with that, coupling to other models, and then bringing in some of the distributed hydrology aspects that are available in NOMP and WRF Hydro into CTSM, things that are not covered by the representative hillslope model. Okay, so that's CTSM. Now I'm going to move on to the PPE project. Again, a big cast of characters involved. I think I've talked about this last year, so I'll just sort of give a brief overview here. We're interested in uncertainty for all aspects, but the goal of the project is to complete this comprehensive, unprecedented parameter uncertainty assessment for the full BGC model. I think people have done this for smaller versions of the model at single points for different aspects of model, like say that's the hydrology, it's just the energy. I don't think it's really maybe ever been done for a full BGC model at the global scale. We want to develop the infrastructure to make this easy to do so we can keep doing this going forward, and hopefully also develop a parameter estimation methodology. We want to then explore the sensitivity of a range of features of the global coupled land system to reasonable uncertainty in model parameter values. So that's the overall goal. This project has 4 phases. Phase 0, which is the infrastructure development, which is really critical. We wanted to do this right from the outset, and I'll go through that in a bit of detail. Then phase 1 will be a set of one at a time parameter ensembles under a range of environmental perturbations. So that's, I think, one of the new features of this, and I'll get to that. Phase 2 will be a Latin hypercube ensemble. We're selecting the most important parameters and use a neural network to develop an emulator of CLM output to help us then move into phase 3 to optimize the parameter sets based on multi-objective calibration targets. So none of this is like brand new stuff. Like, people have done this before. I think what's new here is the scale of the effort and the scope of the effort, and also all the infrastructure that we're building to make this sustainable long run. And in the end, we're hoping to run about a 200-member ensemble of global transient simulations with reasonable parameter sets to really assess uncertainty. And this would be a new thing. Okay, so infrastructure development, we've identified, in quotes, all the CLM5 parameters. It's actually surprisingly hard to identify what is a parameter and what isn't, but let's just say we've done that successfully. There's more than 200 parameters we have identified in the model across all aspects of the model, from the radiation, surface fluxes, hydrology, into the carbon cycle, fire, acclimation. We've extracted all those hard-coded parameters into a parameter file so we can easily manipulate them. So again, this is a big important infrastructure development, exposing all the parameters. And we've cataloged all the parameters and provided initial reasonable ranges in a living document that we can track going forward. So that document just looks like this. It's just an Excel spreadsheet or Google Sheets that has all the parameters listed here. We're just listing a couple that, from the data set. It includes information on the minimum value, the maximum value, as either per expert judgment or the literature. Where it's a PFT dependent value, there's another subtable which will give you high and low values for each PFT. Comments are just things that we're sort of trying to keep track of as we're learning about these parameters, and then a description. So the idea is that this is going to be a living document that we'll release to the community soon. We don't want to release until we're sort of sure it's really in a good shape, so that any user can come in and try to understand what those 200 parameters mean, reasonable ranges, and as we get to the point of actually tuning it up, maybe our calibrated ranges too, calibrated values. The second thing we're doing to be able to do this large scale thing is that we need to run fast. And so to do that, we want to run on a sparse grid. And so Forrest Hoffman and Nate Collier have been running a cluster analysis on transient simulations assessed on mean and internal standard deviation for about 20 different forcing variables and carbon, water, and energy state and flux variables. So what we found through that effort is with about 300 to 400 clusters, you can reasonably replicate the 2-degree global mean and transient model output. So that's good news. With only 300 to 400 clusters then, and we use ILM, I'm not going to get into this to help us understand the clustering, it's fast and cheap. For about, the cost of the model is down to about 4 PE hours per year. So that's really fast. And with the matrix spin up, thank you to Yichi and Chris Liu and others in Yichi's group, with the matrix we can now get the spin up down to about 120 years, which is about a 10x increase in speed and spin up. So this is now possible. We can actually do a full spin up for each different parameter set, which would never have been possible before. And just why people have not run BGC type parameter perturbation experiments. So with about 1 million PRs, we can now run about 2,000 parameter perturbation simulations. And we've reserved a lot of PE hours for this project. So, automation is key here. We want to make everything automated so that others could come back and repeat all this with their focus on whatever they want to work on. So, automated scripts to set up cases, manipulate parameter values, execute and check spin up and conduct ensembles, and do analysis. So all of this we're going to provide to the community very soon, as I'll get to. Okay, and so then I'm only going to be able to talk about phase 1 today, but it's starting off with a 1 at a time parameter sensitivity for all 200 plus parameters. We're doing high-low values, and each simulation will be checked for reasonableness, including things like plant survivability rates. Within some value, we're starting with 30% of the control, reasonable maximum LEI, GPP and LH within plus or minus 30% of the observed. And we've seen in the past that if you go to new parameter sets, plants can die. And so we're just trying to ensure that the parameter sets we use aren't killing all the plants. If a run with a particular parameter set doesn't pass that check, then we'll constrict the parameter range and run again. And then we're going to run parallel ensembles with environmental perturbations. So for each parameter set, high and low values, we're going to run 1850 climate, future climate, 1850 CO2, future CO2, and adding NDEP. And then we may also do some last glacial maximum conditions to help out with the paleo group. And again, if we find at the low side in particular that the parameter ranges result in a bunch of PFTs dying, we'll constrict the parameter ranges and start again. And so we are about to kick off this experiment. We've literally been having emails this morning about kicking it off. So we do think that within hopefully a month or so, we'll have this 1 at a time set of simulations done and then move on to the Latin hypertube aspect. And since I'm a minute over time, I will stop there and not go through. I do go through the next steps and the rest of the slides, which you'll have available after this meeting if you want to see, but we're not there yet. So I'll stop here. Thank you.
Great, thanks, Dave. Briefly, Sam, are you on, Sam?
I am, yeah.
Cool. So Sam's got a couple shout outs already, but Sam wanted to reintroduce himself to the group. And then after that, we can have a discussion, questions about anything that Dave or I presented.
Thanks, Will. Good morning, everyone. So for those of you who don't know me, my name is Sam Levis. But as many of you already know, I worked on NCAR's CLM development team for many years, and I was also CLM community liaison for most of that time. What I wanted to make sure everybody knew was that in the last few years, I changed my role from employee to consultant / contractor. And at the moment, I expect to have availability later this year. So please get in touch with me whether you need help soon with an existing project or will need help with the project that hasn't started yet. You can reach me at slevisconsulting@gmail.com. I can paste that in the chat right after. I am able to help with the whole range of modeling work, so model development, model runs, model inputs, model outputs. If you have difficulty completing a task for an existing project, or you are thinking ahead to a project that hasn't been funded yet, just feel free to reach out to me. So again, it's slevisconsulting@gmail.com. And thanks, Will, for giving me a minute to share that.
Great. Yeah, I dropped Sam's email in the chat. Yeah, so do folks have questions, comments, concerns, or feedback on any of the kind of accomplished or upcoming stuff that we're working on? Yeah, Sanjeev, go ahead.
Yeah, but sorry I was late, so I missed first talk, but I saw the Dave's talk. It was very good. Thank you. And I'm really excited to try some of these CTSM work configuration. So yeah, I'm excited to see that it has now come online and it is working. I had a question on your last slide. Can you show up again?
On Dave's last slide.
Yeah. So here, if I read it correctly, like environmental perturbation are for 1850 and then SSP 3.7. So does it include the present climate, or are we excluding the present climate, or I'm not reading it correctly?
These are the environmental perturbations. So the control simulations on which would have been on the previous slide, the initial ensemble is at present day. Okay, so present day CO2, present day everything, oxygen deposition, high low perturbations. And then we are going to repeat those simulations, that full set of parameter perturbations at 1850 levels at SSP 3.7. So the idea, and these other things, CO2 and nitrogen, the idea is then we get to evaluate not just the impact of the parameters on present day climate, but also on the response to a perturbation, whether that's in CO2 or climate. And because that's the thing we really want to know, we don't want to like eliminate or ignore parameters which may have a small impact on your mean state, but have a big impact on your response. Does that make sense?
Yeah, that makes sense. Thank you.
Great, Stephanie.
Good morning, everybody, or good evening, depending on which time zone you are. My question is related to the WRF coupling. So will this also include chemistry in the atmosphere or not?
You mean the WRF chem?
Yeah.
I don't think that works right now, but that is on the goal. I don't 100% know. Maybe Megan could, if she's here, could answer that, but I don't believe that would work straight out of the box.
So the WRF chemistry currently with CTSM doesn't work because there are like some coupling of some of the fields from WRF chemistry, like dust or black carbon that are not coupled to CTSM for now, but that's like on future to-do list for us, and we're hoping to accomplish that pretty soon. But no, the capability is not there now, but it will be there soon.
Yeah, if you think you would use it, that might inspire us to move it up the priority list. So shoot us an email if you feel like that might be a priority for you.
Hey. Dave, did you have yeah, go ahead, Yichi.
Dave, in your slide, in your talk, you mentioned that Now you can have 120 years for spin up with a matrix approach, which is much faster than what Chris worked out.
Yeah.
Can you explain that?
Yeah. So the methodology we actually came up with is we're skipping. This is going to be a detail for people who don't know, but it's kind of interesting. Is there's like it's like a 4-step process for matrix, and we actually found that you can skip steps 1 and 2 and run our old accelerated decomposition mode spin up for 20 years instead of steps 1 and 2 of the matrix. And I think the reason that works is that comes very quickly, gives you a good estimate of GPP and NPP. And it's actually faster than the matrix. And then once you have a good, robust estimate of your NPP, then matrix does much better than the old method in terms of equilibrating the rest of the system. So it's actually a merging of the two methods is what's leading to this.
Maybe we need to have more discussion with you on
Yes.
Thursday. Cai Juan going to make a presentation. Actually, that's pretty much based on the quiz results.
Yeah,
Okay, thanks.
we should talk. But yeah, that was a nice sort of thing that we figured out when we were sort of exploring. I can't remember where we got the idea to try that, but it worked out really well. So
wonderful.
Yeah.
Well, thanks.
Yeah.
Dave, did you have a comment or question?
I just wanted to make a clarification about the quote unquote shout out to Sam for the conservation check and to say it was not just water, it was all components. So the carbon, nitrogen, water, and energy, I'm not sure, but because energy is a little harder, but and just so people aren't being worried, we were checking at the column level previously. This is now the grid cell level, so it's accounting for transitions better, and it's accounting for everything that's going on in all our different columns. And we did uncover several little minor bugs. So, it sounds like a small thing, but in actuality, it should make the system quite a bit more robust going forward. It's catching new things, I guess that's.
Sanjeev, do you have another question?
Yeah, it looks like kind of very exciting to see that the WRF side of applications. Okay, is there some training opportunity available for the students to send who can get some training how to run the system, or do we need to follow, or are you planning to offer a tutorial or something sort of that one? Or like what's a kind of headway in terms of getting started on this kind of new CTSM system?
You mean WRF CTSM?
Yeah.
The user's guide is pretty robust, and it's actually not that hard if you know how to run CTSM at all. Most things will be familiar. It's people who've never run CTSM before who might see some things that are like a WRF user who's been running WRF NoMP might get a little bit confused. Faye occasionally would get confused. Faye Chen, who's the leader of NoMP. So I think I would recommend you follow the user's guide, which you can get to from the GitHub site. If anyone wants it, I can send an email, but it's easy to find. We'll do the same thing for the new workflow in terms of surface dataset creation when that's ready. And we will have another CTSM tutorial at some point, and Will didn't mention it, but I'll just say we're thinking we want to wait till we can get back together in person. So that's probably looking until 2022. But we'll almost certainly would introduce WRF CTSM in that tutorial. But I don't think we have anything planned before then. That said, we want people to use it. So if you're running into any problems, we will try to help people, because the more people who use it, the quicker we're going to learn, what the problems are.
Thank you.
Oh, and Nathan just put the link to the user's guide in the chat. Thanks, Megan. Andy's asking about a WRF tutorial for CTSM users. Yeah, that's a good point. again, I think I would start off with try to follow the guide, and if that's not enough, frankly, I can't give that tutorial because I don't know what's going on. I was able to successfully run it, but yeah, it's a good point, Andy. I don't know.
If there is interest, we can kind of coordinate with the WRF group to have like maybe a day workshop in the WRF workshop, a day workshop of just running like WRF CTSM. Dave Gill told me about that. If there is interest, we can set something like that up for the users, but it would be for mostly geared towards WRF users to be familiar with CTSM. And I think Andy is saying the other way, so.
There's a question in the chat. Should I address it, Jackie?
Sure. Do you want me to read the question, or will you just read it out loud?
I'll read it, yeah. So Julie is asking whether the carbon equilibrium check, whether we've done it for all 2,000 parameter instances. Well, there's actually 200 parameters in the high-low values. So we have not done that. We tested for 3 or 4 parameters, for 2 parameters, and that was the general rule of thumb. Within our process, we will have a equilibrium check for each time we run. So Daniel and Katie have been setting up some really nice scripts to automate all this. And so, at the end of the 120 years, we will check for equilibrium. If it's not there yet, then we'll extend for just that particular parameter. So I don't expect all of them to fall in to satisfy the criteria. I also don't want to get hung up on this. If we're a little bit more out of equilibrium than we, are really strict criteria, I think we've already relaxed it a little bit for the purpose of this. But yeah, that's part of the process. We'll also, the nice thing about that, we do anticipate that some of those 200 parameters are actually not even being used. It's sometimes hard to tell in the code. And so one thing we'll do is be able to find out which parameters make any difference at all, and throw out the ones that don't matter. So this has got multiple benefits, this project, I think, in terms of infrastructure and science advances.
So Dave, has there been discussion of doing a PPE for fates?
I can let a face person answer.
I just was saying, Ryan and I were talking about this yesterday. I mean, we certainly want to. I guess maybe a first step would be in being really clear, like, in the spreadsheet, which parameters are common to fates and which ones aren't. I don't know if that's already in there, but it seems like a thing to do.
I don't think it is, but yeah, we could easily make a column. And the way to do that might be, rather than going through the code and trying to figure it out, just run the fates, a little mini fates ensemble, and see which ones actually change something. Because it could be kind of painstaking to go through and figure out each parameter individually. Just run a 5-year thing and just see which one does something. Yeah, we could add a column. I think, Jackie, we'd want to do this, but we want to make sure it's pretty robust in CTSM, right? That's the goal, is to get through all these kinks. And there's been a bunch of kinks along the way already, which I didn't get a chance to go through. But each step of the way we're learning and putting in new checks and new things. So.
Yeah, I think it'll be useful to have this methodology and build off of it for fates. And then depending on what version of fates you use, so there's another layer of complications when you switch over to fates.
It could also just be that the fast mode is a really nice thing for fates. We all run that for identifying clusters and
Great. Do folks have other questions? Charlie, go ahead.
Yeah, actually, Dave, I had a question for you for on those cost estimates for the WRF CTSM. So that was the full. That wasn't just the cost of the land model. That was the cost of the full model that went up by like a 40%.
As far as I understand, it was Sam and Megan who gave me those numbers. Yeah, it's surprising. I don't quite understand how it could be that big a contribution.
Yeah, that's a lot.
Yeah, exactly. So it is preliminary. So I'm a little bit skeptical, but I wanted to raise it as a point that it's something that we need to be conscious of.
And is it CPU hours or is it clock hours? I mean, is it parallelizable or not? Do you know? I
don't think that was Sam was doing a very rough estimate, like how long it took to run. So it's not even really a CPU hours, but I don't know whether there's any possible gain you can get by a different, PE layout. I don't know anything about WRF, so that's again another thing that maybe we can find a configuration that's a ton faster. Yeah, I think the lesson I'm learning from this whole project, right, is that you can say you want to do something, and it sounds so easy when you just say we're just going to couple CTSM to WRF. How hard can that be? And we're gonna merge models, and then of course the devil is in the fact that there's 1,000 details that you need to worry about. But we are ticking off a lot of the big ones, and the next big step. One of the next big steps is really finding ways to get the weather community to consider adopting this. And that's still remains a little bit of a mystery, but having a paper will help. And we probably really realistically need some resources to get somebody to really focus in on that weather problem. Like I mentioned, the weather forecast problem, which is it has to really do well in that configuration where you're looking at the 5-day, 7-day forecast. Until we prove that, it'll continue to be not that well used, I think.
We have a question
Katie, go ahead.
from Katie.
Yeah, shifting gears a little bit. Will, you mentioned CESM Lab or CESM Labs, the cloud, running CSM on the cloud. And I know I've heard Brian Dobbins talk about this, but if you or others on the call could maybe put in the chat like a GitHub link or whatever the most up-to-date references for that, because I do get people asking questions about wanting to run CESM with limited resources. And so if folks have kind of up-to-date references for those, that would be helpful.
Yeah, it'll take me a minute to find it. Right now, it's just it's on Docker, so that's the best way to find it. And the challenge, and it's right now it's CESM 2.2 that he has built in there. And the challenge that Brian was kind of shocked with how much data the land model needs, especially for global runs. And so that right now that's the bottleneck, is that you can run the model, you can even run the global model on your laptop, but first it has to download all the data, and that's the part that's kind of prohibitively expensive at this point. So at least for CLM or CTSM users, I'm optimistic that these single point runs at Neon sites and maybe eventually the Plumber Towers will be a nice way to not have to download global data sets to be running. But yeah, maybe after I'll have to dig through my email and find that Docker.
Yeah,
Andy
Fox just put something in the chat. Might be
okay. Cool.
Yeah,
and right now it's kind of a beta version. At least last I tried it, that Brian put up, but he was looking for people to kind of give it a whirl.
Cool.
Yep.
So Will, I think carrying on with that question about Docker, Julie asks, why not include it on the GitHub wiki page?
Yeah, that's a good idea.
Yeah.
For now, yeah, that's an easy place to put it. That's a good idea, Julie. Dave, I know we've talked about this in CLM meetings, but have you had a chance to talk to Gab or anyone else associated with Plumber if we'll be able to distribute or keep or kind of continue to use the Plumber forcing data for our own purposes?
I haven't talked about distributing. I don't see why we can't use it, definitely on Cheyenne.
Yeah.
There is always questions about distributing. I guess they wouldn't really want us to distribute, but yeah, I get if someone wanted to use it, if we found there was a need for it, then I could ask, but I'm not 100% convinced there's going to be a broad need for that.
Mm.
And the other issue is whether or not they will give us the observational data, which would make it a lot more useful if we had the latent, the turbulent fluxes and all the OBS data.
Right.
And I did ask about that at one point, and the answer was ambiguous. So I probably need to circle back around and ask. But we should actually put a link somewhere here to the. Actually, if Keith, if we can look at modelevaluation.org, so this is the site that Gab Abramovitz is building and maintaining, where you can all the data analysis happens for CLM and other models participating in Plumber. Is available. I don't know if it's interactive or whether you have to be a member or not. But if it's interactive, then you can at least go and start looking at all the different tower site results from CLM up there.
Yeah. Sean had a question in the chat. There's a lot going on in the chat.
Yeah, sorry. Maybe I'll just mention it rather than try to go through because I hit enter too soon. My main question was the neon sites. Did they ship with the surface files extracted for those locations as well? Because those would be perfect test cases for Docker.
Yep,
because the data demand to be tiny.
Yep. Yeah, that's our plan, is to provide surface data sets and domain files along with the atmospheric forcing data. And then eventually build on the capabilities through CESM Lab to grab evaluation data off the Neon data portal. But the first step is so right now the workflow will be that Neon has a Amazon bucket where you can download the data, download modifications to the surface data set and the gap-filled atmospheric forcing files from the tower sites. And those should be going live pretty soon. I think Neon just released a revision of their Flex Tower data. So that's what have been kind of waiting for. And Dave Durden is the collaborator at Neon who's doing a lot of this work. And then the idea is that, so Jim Edwards has built the pipeline for us to be able to query that Amazon bucket, download the new monthly forcing files that we need for CLM, and then also grab the data that we'll need to modify the surface data set. So then on the NCAR side, we'll be able to kind of provide both I don't know if we're actually going to provide the atmospheric forcing data or if other users can just go grab it from the Amazon bucket themselves, and then the surface data set and domain files to run the single point towers. So that should be, hopefully it will be pretty light and fast. The other thing that we'll provide is initial conditions files, because for the kind of baseline CLM runs, so we'll have the model spun up and then users, these will all be BGC runs because we don't have LAI data from the Neon sites. So there'll be BGC runs and we'll have those initial conditions files also available.
Thanks, Will. And I just want to note that Bill Sachs put a link in the chat and an invitation for people to add an issue for improvements or documentation, anything that's needed on the SCOMP CTSM GitHub page. And so Bill actually opened an issue about adding the Docker instructions to the wiki. So feel free to jump in.
Yeah, and I guess I'll second that. It really is helpful if people have questions, if they have problems, if they have new model developments. We're definitely using issues on GitHub as our way of tracking that. And every week we look at the new stuff that's come in, and especially Bill and Eric, really keep on top of what those new issues are. So that helps us out a lot to make sure we're providing useful tools for the community. Jackie, are you seeing anything else on the chat that we should repeat, or?
No, I think there was a lot of chat about Sean Servan's question about Docker and its relationship to Neon, and so I think you addressed that. And then Eric mentioned that the data for Neon would be really fast to download, and whereas the global forcing data is much larger, and so it's problematic for a normal user.
Yep. Yep. Yeah, and just like with CTSM WRF simulations, like these Neon tower simulations will be, if people are interested in using them, I think getting university folks on engaged in using the tools as they're being developed to be really helpful. It's exciting that 3 different NSF directorates are investing in it, but that also, but it's also a 1-year project. So we can, if there's new features that people are wanting or other things to add, I think that would be helpful to get that input early and often.
And then Keith Olson put a link in there to the modelevaluation.org website. So that came up. Keith, did you want to say anything about that, or you just wanted to provide that to everyone? Okay, so that's the website if you want to look at it. There's nothing to add. I think it came up in just the more general discussion. So thanks.
I got a question, Jackie, from email, and it's an interesting point. So it was from Linnea, and so hopefully she's okay with me airing it here. But she asked about sort of in the PPE when we have correlated parameters, what are we going to do? And she gave the example of Jmax and VCmax. And so the short answer to that is we are going to try to consider correlated parameters as a second step. So we know of a few sets of correlated parameters which we're already going to try to include as another kind of essentially member in the one at a time ensemble. And so we're going to keep building out as many of those as we can without getting too bogged down. And then as we go into the next phase where we're trying to identify the most important parameters, we may choose correlated parameters as a single parameter in certain instances. But that is an important question, and I wanted to raise it in front of people because it is an issue with these one at a time parameters. So we're aware of it. We don't 100% know how we're going to deal with it, but we're going to try out a few things.
Maybe we have time for, I don't know if Sanjeev, if you had a question. Pretty soon, Meg, if you want to hop up and start opening up your presentation, get back on track for this.
Yeah, it was not the question, it was a comment like, yeah, there are some of the discussion going on the chart related to the Docker version. And even like we have tried the Docker version, and yeah, the main issue is when it start downloading the data, and then the computer will start kind of getting crashed. So it's too much of the data. Having run CLM even outside the NCAR or even with it has been difficult for me, at least for last 3 to 4 years. So now I've started thinking about like a hybrid version of the model where some of the computation can be done at the NCAR machine, but it's still like, yeah, in that case, you may not need to download that terabyte of the data that you just need to run the model. So is there some thought process going on? Like, yeah, we all talk about the cloud, but yeah, I have not been able to make significant progress in that direction. So having seen for the last 3 to 4 years, now I've started thinking more into hybrid version. So that is something that land model group would be interested in developing and making some progress.
Yeah, I think through this NEON project, it's been fun to interact with Brian Dobbins more, who's doing the CESM lab work, and I think as much feedback as users can provide him on what their needs are, I think is kind of the critical part now. Yep, but yeah, he totally gets it that the land data requirements are pretty large, so it's on his radar. I don't know what a convenient fix is for that, but
thank you.
Yep. Meg, do you want to go ahead and share your screen? Yeah, so we've got 2 more speakers before a break, and then the CGD seminar, and we'll come back after lunch. But up next is Meg Fowler, who's a new project scientist at NCAR, talking about land-atmosphere interactions.
Cool. Thanks, Will. Can you see the screen okay? Cool. Okay. So today I'm going to talk a little bit about some changes we're seeing in land-atmosphere interactions across different model versions of CESM. And this is work that I've been doing primarily with Dave Lawrence and Rich Neal, but I also want to thank Isla Simpson and Cecile Lene for their help with these simulations. So, see if I can, here we go. Obviously, I'm pretty sure this group doesn't take a lot of convincing, but there are really wide-ranging impacts of land-atmosphere coupling. Strong regions of coupling can influence everything from precipitation, cloud cover, hydrometeorological extremes, things like floods, droughts, and heat waves. And recognizing that importance has helped spur some new efforts at improving how they're represented in global climate models. And so I just want to mention briefly the CPT that Dave and I are a part of called CLASP, which stands for the Coupling of Land and Atmospheric Subgrid Parameterizations. And the goal is to take advantage of the fact that there is subgrid heterogeneity on the land side that can help inform what the atmosphere does. And so how we communicate that up is really what we're trying to figure out as part of CLASP, with the ultimate goal of improving the realism of how these interactions are represented in a global coupled climate model simulation. But before we really dug into that, we started thinking about, well, how sensitive is coupling in CESM to changes that were made without an explicit intent of changing the coupling strength? So if we're going to go through this effort of trying to improve the coupling realism, what has it been doing with its baseline sensitivity, essentially? So the way that we're thinking about that is through the LOCO framework, which I've nabbed a figure from Santinello et al. In 2017 to illustrate this in a bit more detail. So the way that we think about land-atmosphere interactions is really as a cycle. And so there are anomalies in soil moisture that can feed into surface fluxes. Those affect the boundary layer, precipitation, clouds, and then those then feed back to the surface through low-level temperature and humidity. What I'll focus on today is kind of 2 legs of this process: the atmospheric leg, which I'll look at as considered how surface fluxes influence boundary layer heights. And then the terrestrial leg is how soil moisture actually influences those surface fluxes. We can quantify that through something called the coupling index, or CI for short. Essentially, we're looking at the covariance between each of these 2 variables, whether that's sensible heat flux and boundary layer height or soil moisture and flux, normalized by the standard deviation of kind of your driving variable there. To give you an idea of what this looks like a bit more concretely, this is from Paul Dermeyer and his group's paper in 2014, which looked at a CMIP5 multi-model mean of this coupling index. The atmospheric leg is on the left. And so here we're looking at the sensible heat flux relationship to a proxy for boundary layer height. This is the pressure level of the lifted condensation level. And you'll notice that these areas of kind of reds and dark browns, these are where your coupling is stronger. So there's a direct relationship between flux and boundary layer height. And it's picking up a lot of the classical hotspots we think of for coupling. So the central US, equatorial Africa, and parts of the Indian subcontinent. For the terrestrial leg on the right-hand side, this is where more negative values equal stronger coupling. So there should be an inverse relationship. And we see that again highlighting a lot of these same regions as we would expect. So the question then is, how has that coupling index actually changed across different versions of CESM? So narrowing down to just one single model. We're looking at this through a series of AMIP simulations. We have daily output from 1979 to 2006, and we're looking at CESM2 and CESM1, and then kind of subbing out different versions of CAM and CLM to understand which model components are really driving changes. And I will note here that I'm focusing on boreal summer, similarly as these figures are showing above. So to cut to the chase, CESM2 has lowered overall coupling strength relative to CESM1. And so here we have the atmospheric leg again on the left-hand side. CESM2 is on top, CESM1 is on the bottom. And CESM1 has a lot of these really strong coupling strengths showing up at kind of odd locations like the boreal forest in northern high latitudes. And that's really been reduced quite strongly in CESM2. Similar story on the terrestrial side of things, where we're having pretty strong coupling all over. That's been reduced, particularly at high latitudes and some of the mid latitudes in CESM2. The question then kind of arose, well, is that a good thing, or have we gone the wrong way in terms of realistically representing coupling between land and the atmosphere? So this can be kind of hard to address from the atmospheric segment. We don't necessarily have great observations of things like boundary layer height, but at least from the terrestrial leg, we can kind of say that it appears that this is moving in the right direction. So what I've done is compared the model simulated coupling index to a series of FluxNet observations at 115 stations. These all have at least 3 years of June, July, and August observations for sensible heat flux and soil moisture at depths of no greater than 20 centimeters. So the model we're using 10 centimeters. So they're roughly comparable. And each of those towers is plotted here in a black circle. Just by eye, you can see that some of these colors are lining up a bit better, especially through parts of northern Canada. My favorite point is down here in Australia, which has changed quite a bit. And the mean absolute bias has decreased. So if we look over all of these 115 stations, we do see that in CESM2, JJA coupling strength bias has decreased a bit in CESM2. Now that doesn't necessarily tell us anything about why those changes are happening. So it's kind of what I want to try and address next. So if we kind of look at zonal means, which is what I'll show for the rest of this talk, here we have in black CESM2, which is a combination of CLM5 and CAM6. In blue is CESM1, which is a combination of CLM4 and CAM5. And again, you'll notice that we just see this general decrease in coupling strength over a lot of the mid latitudes and some high latitudes. Again, for the terrestrial leg, as we become more positive, that coupling index is weakening. And if we start subbing out either the land or the atmospheric components, we start to see some interesting things. So in this simulation, this is combining CLM5, so the same land model is in the black line, and CAM5, so the older atmosphere model. What's really striking is that the red line is really similar to the black line, which would indicate that the change between CLM4 and CLM5 is pretty significant. The change between CAM5 and CAM6, not necessarily as much for a lot of latitudes. Just to reiterate that, here's a simulation with a slightly different land model, but still older, CLM 4.5 and CAM6, so the new atmosphere model. And it's actually showing a lot more similarity to the blue line. So even though you're looking at CAM5 and CAM6 in green and blue, they're much more similar than if you were to look at CLM5 and CAM6 versus CLM 4.5. So it would seem that the updates in CLM5 have pretty significantly contributed to weakening both the atmospheric and the terrestrial leg of the coupling index. And then the last question that we wanted to address was, okay, say it's in CLM5, what exactly changed that's driving this weaker coupling so that we know going forward? So for these simulations, I'm doing sets of 5-year sensitivity experiments. These all use CAM6, so the latest version of the atmospheric model, just from 1979 to 83. And these are basically the same lines that you saw before. CLM5 is in black, CLM 4.5 is in green. And so what I'm wondering is what kind of moves the black line up to the green line, essentially. So if we were to run CLM5 and revert, a series of changes back to what they were in CLM 4.5, can we isolate what's driving this? So in large part, a lot of this is coming from the implementation of a dry surface layer, and that's particularly noticeable here in the tropics and some of the lower mid latitudes. The blue line is super similar to the green here, almost identical at some of these points. So just that one change, keeping all other CLM5 options consistent, does decrease coupling strength pretty noticeably. We've tried a few other variables, and so just to kind of illustrate some of this, we've also looked at the implementation of plant hydraulic stress, the fraction of precipitation that's intercepted in purple and gold. Those haven't necessarily moved the bar as much as I would have hoped to see. And so those don't necessarily explain why we're seeing these decreases in coupling strength in CSM2. Just to note, one that does show a bit of a signal here, this is where we've reverted back changes in soil thickness and root profiles. And at least in the terrestrial leg here, from maybe 50 to 60 degrees north or so, that does show some decrease in coupling strength. So long story short, most of this change for lower latitudes seems to be coming from the dry surface layer, but it's still a little bit unclear what's going on at the higher latitudes. So that's still an area of ongoing work. But just a few key takeaways from the talk overall is that CESM2 does show a generally weaker coupling strength in JJ than CESM1, at least as measured by the coupling index. It appears to be slightly more realistic in CESM2, that weakening for the terrestrial leg, but again, for the atmospheric leg, we haven't really evaluated that yet. It's a bit more complicated. The decrease in coupling seems to come primarily from updates made in CLM, and that's true even for the atmospheric leg of the index. So even though we're looking at the relationship between soil moisture, sensible heat flux, and then the boundary layer height, an atmospheric component, those changes are really coming from the land model. And just to highlight, that really does suggest the importance of assessing coupling from both an atmospheric and a land perspective whenever these large model updates are implemented. Try to understand if we're improving things or not. So with that, I thank you for your time, and feel free to shoot me an email if you have any questions too. Thanks.
Meg, can I ask a question?
Yeah.
How hard is that coupling metric to develop or evaluate? Like is it off the shelf? You just plot it up, or is it kind of involved?
Yeah, the coupling index is my favorite because it's super simple to plot up.
Okay.
And so Ahmed had this, the coupling metrics toolbox is super helpful. And so the coupling index can be ported really easily into like a Python notebook, and you just, 3 lines, run it, you're good to go. Yeah, cool. You just need daily data is the only caveat I would say.
Okay.
Isla, do you want to ask your question?
Yeah, I was just wondering if you could explain a bit more what the dry surface layer is and what that means.
Yeah, so Dave's the expert on this, so feel free to interrupt if I get this wrong. But my understanding is that the dry surface layer is like the surface lens of the soil. So prior to having that in, it would be a little bit easier to evaporate moisture from the soil itself, when in reality, there's kind of a lens that resists that a bit more strongly. And so the dry surface layer represents that.
Okay, thanks.
Yeah, it captures the subgrid, in this case, vertical, less than 2 centimeter impact of a skin layer of dryness, which forms a barrier essentially to evaporation. And it has the additional benefit that it shows much better annual cycle of the terrestrial water cycle in many places. So total water storage from GRACE. So there's some additional evidence that it's doing something sensible.
Yuri, do you want to go ahead?
Yeah. Hi, Meg. I'm just wondering about this station evaluation about the soil moisture. Is that a kind of static evaluation? I mean, for the coupling strengths, I think maybe the temporal dynamics of the change in the soil moisture could have very large impacts on the coupling strengths. Thanks.
Are you thinking like over multiple decades it could be?
Or in the annual, or yeah.
Yeah, so I will say we're only looking at June, July, and August, but I haven't done any normalization to the data other than isolating just the summer months.
Okay, thanks.
Yeah, that's a good point.
And Stephanie?
Hi, Meg. I was wondering if, regarding to the land model that you were testing with, if it is connected with what Will showed us earlier about the change in leaf area index between the different land model versions, if this could explain part of what you're finding.
Yeah, I haven't looked at any leaf area index changes. I don't know. I guess I don't know.
Meg, aren't these specified phenology runs?
They are. Yeah. Yeah, this is specified. So in that case, it's not interactive. Yeah, probably not. Thanks, Dave.
Great. So I don't know if we move on. So our next speaker is Marisa Legue. And if you can share your screen.
Can you see it?
Yep, that looks great.
Properly?
Thanks.
Super duper. So I'm going to be talking about how terrestrial evaporation impacts surface temperatures, specifically over land, and how there's competition between warming and cooling that we see from this. So I guess the main sort of setup for this is that the land isn't the ocean. Surprise. There's lots of differences, specifically changes in heat capacity, topography, surface properties, and the capacity of land to store water. And it's this capacity of land to store water that I'm really focusing on today, I guess. So if you're the atmosphere sitting over the ocean, you effectively have as much water as you want to evaporate. That will never be what is limiting how much evaporation you get from the ocean. Whereas if you're over the land, the total amount of evapotranspiration you can get from the land surface is strongly going to depend on how much water is actually on the land in the first place. And you can see this if you just look at annually averaged latent heat flux from the surface. So you've got the more orange colors are showing higher values and the lighter yellow colors are showing lower values. And you see that you do get much larger latent heat fluxes over the ocean, no surprise there, than you do over the land, but you also get a lot of heterogeneity over the land surface. So places that are really wet, like the Amazon, get a lot more latent heat flux than if you're sitting in the middle of a desert. And this matters for surface temperatures, obviously, because if you can evaporate, then you can cool the surface via latent cooling. So if you have higher latent heat fluxes, then you're going to be comparatively cooler than if you have low latent heat fluxes. And you can see this in observations. So the top is a false color image of a pinyon juniper forest, where the green colors are showing you where the trees are, and the kind of tan color is showing you dirt. And then the bottom image is the same photo, but an infrared. So it's telling you the surface temperatures, where the purple colors are comparatively cool, around 24 or 25 Celsius, and the dirt is the really bright orange colors, and they're reaching 60, 70, even higher degrees Celsius. So if you have water and you can evaporatively cool, it means you will have a much lower surface temperature. And we see this in models too. They can represent this, which is good. We can do the surface energy budget. So in this paper from 1982, they basically looked at the difference of a simulation where the soil was just given as much water as it wanted compared to a really dry soil simulation. And these contours are just showing you that you end up with much higher temperatures. That's what all the tight contours over the continents in the bottom plot are, if you can't evaporatively cool your land surface. Comfortingly, CESM does this also. If you turn down evaporation over land, you will end up with warmer surface temperatures, and that's what these sort of teal and yellow colors are. What you can also see in CESM is that these sort of warming patches from the land, they can blow out over the ocean and lead to ocean warming as well. So all of what I've shown you is really just a consequence of balancing the surface energy budget. If you decrease evaporation, then the energy that used to be going into this latent heat flux instead has to go into warming up your surface, so you get higher sensible heat fluxes and higher long wave radiation coming out of your land surface. So if we're just thinking about this from a surface energy budget point of view, we would expect that this response to decreasing terrestrial evaporation shouldn't have anything to do with continental configuration. So with that, we're going to leave the real world and move to this very idealized setup of worlds where we have these various idealized continental configurations. So we've got one that looks kind of like the real world, and then we've got these 5 blocky continent simulations. So we've got one where the whole northern hemisphere is one giant continent, and then one where we've got most of the northern hemisphere is a giant continent, and then we do a simulation where we split that up into 3 kind of chunky islands, and then we further decrease the land in the northern hemisphere, so it's about half of the northern hemisphere's land, and we break that up into 2 chunky continents. And we're going to look at what happens if we suppress evaporation in these 6 different configurations. And I'm doing a pretty drastic reduction of terrestrial evaporation here. So effectively, you can imagine this as kind of paving all of the land with a really well-drained parking lot. So we're making the bucket super tiny so the land just can't store any water, which means that you're going to have effectively no terrestrial evaporation compared to sort of normal looking land where you have a regular sort of semi-realistic amount of evaporation coming out of your land surface. I'm doing this not in CLM, full disclosure. I'm using a very idealized climate model. It's called ISCA. It's really easy to move continents around in that model, which is why I'm doing it. That comes with some caveats, such as it's just sort of bucket hydrology for the land surface, and clouds are invisible. It can do precipitation and all that, but clouds aren't radiatively interacting with the model. So if all we cared about was the surface energy budget, then we would expect that as we go into these simulations and suppress terrestrial evaporation, the land should get warmer. Obviously, that isn't what's going to happen, or I wouldn't be wasting everyone's time telling them this over and over again. So what we see is that if we go in and suppress evaporation in each of these continental configurations, what we get is this sort of wide range of temperature responses. So red colors here are showing you places where turning off evaporation means the land gets warmer, and blue places are telling you places where the surface temperatures get cooler. So there's sort of a lot going on here, but some things to take away are that, you know, we do see warming over land in these sort of pretty specific patterns, but we do see also these big swaths of the land surface that don't warm. And these are places that in the sort of climatology of the regular simulation, they're deserts. So they don't have any water available to cool themselves down in the first place, which means that they have no latent heat flux in the first place, and then we turn down latent heat flux, so it's still just zero. So there's no sort of local warming coming from that. Whereas the places that are red are places that normally have water available to evaporate, and you're turning off that latent cooling. So you can see sort of the real world deserts in our realistic configuration, and also the subtropical deserts in these idealized continental configurations. The other thing to notice is that the larger your continent, the larger your big desert areas are in the first place. So you don't get as much warming if you have more desert, which is what happens when you have a really big continent compared to the same amount of land split up into little chunks. And then the glaringly obvious problem child of these simulations is this Northland one over here. This is actually the first simulation I ran, and when I plotted it, I was convinced I plotted it upside down, or like the control minus the experiment instead of the experiment minus the control. And then I was convinced that I ran the simulation wrong, but finally I convinced myself I had indeed done the simulation right, and suppressing terrestrial evaporation here actually does make the land a whole lot cooler. So obviously we need to be caring about more than just the surface energy budget, because turning off latent heat flux should have made the land warmer if that was all that mattered. But instead, we have to think about the fact that water vapor is also a really good greenhouse gas. So what happens in this Northland simulation is that because there's basically no ocean, well, there is no ocean in the Northern Hemisphere, when you turn off evaporation from land, there isn't any source of water vapor to the atmosphere. And if you have a really dry atmosphere, then long-wave radiation from the surface doesn't get absorbed and re-emitted back to the surface. It just goes shooting out the top of the atmosphere, so you lose all of that energy. And if you compare that to a very moist atmosphere, then as you have long-wave radiation emitted from the surface, it gets absorbed by the atmosphere, sent back to the surface, and this is just the greenhouse effect. And water vapor contributes in the present climate about half of the modern greenhouse effect, so it's a really good greenhouse gas. And what we did in this Northland simulation, when we turned off terrestrial evaporation, is we basically killed the water vapor greenhouse effect. And that cooling from that reduction in long wave trapping was way bigger than any local surface warming you get from your surface energy budget response. Of course, in the present climate, we don't live on a giant continent covering the entire hemisphere. We have lots of ocean at every latitude. So there's not really a risk of depleting the atmosphere of water vapor. But that's not the case in this more idealized simulation, where we just don't have any source of water to the Northern Hemisphere. So what this means is we can kind of think of the response of surface temperatures, particularly on land, to suppress terrestrial evaporation as a function of how much total land area you have and how big your continents are. So in our first sort of two-patch land simulation, where we had small continents and turned off the evaporation there, we ended up with warming over the land surface. But if we stick those two continents together, we still have the same amount of land, and it warms, but it doesn't warm as much. And then if we start adding more land, so we have 3 big islands, it's a slight warming over land, but if you shove those 3 together, you end up with net cooling. So now we're starting to see that this cooling from the water vapor greenhouse effect is starting to dominate over our warming from our local surface energy budget response. And of course, the Northland simulation is super, super cold, and the surface energy budget doesn't stand a chance against the collapsing of the water vapor greenhouse. So colder air from less water vapor means less long wave down over the oceans in this simulation also, which is why we see this sort of broad cooling over the water. But mostly what I'm interested in for these simulations is the temperature response of land. So the total land area matters, how big your continent is matters, and the location, obviously, of your land is also going to matter. So if you put a big tropical continent over your oceans where you get the most evaporation, you're going to get a lot more cooling than if you put some big continents over your poles where you can still just get plenty of water vapor evaporated from your tropical ocean, get that up into your atmosphere. The real world is sitting sort of somewhere towards the left of this plot. So it looks a little bit more like this idealized 2-island world if you squint. And also we just ran the simulation. You can see that you do get warming over land. But there are some pretty major caveats to this result. So in these idealized simulations that I'm showing you, the clouds don't have any radiative effect. And we know that land evaporation matters for clouds and changes in clouds matter for surface temperature. So that's a big missing piece of this puzzle. And these were pretty extreme evaporation changes that I imposed here. And we also don't see these sort of pushing out of warm air from the continents over the ocean that we see in our more complex models. So if we wanted to understand this realistic effect a little bit better, then there's sort of two pieces we would care about. We'd want to know how much this change in water vapor is affecting long wave coming down at the surface and what the role of clouds are. So you could get at the long wave piece using a radiative kernel in the atmosphere. You can just ask how much this change in water vapor should change downwelling surface long wave. That's a thing you can do, but these trade-offs between your surface latent heat flux and this water vapor effect are also both going to be modified by cloud processes, and that's going to matter for your surface temperature, and we're not representing that at all here. So what we can do to sort of dig a little bit deeper into that very quickly is we can look at what happens in our idealized model when we turn off evaporation over our continents. We get less total column water. So that's the brown colors here. This is integrated water vapor in the atmospheric column. And that results in the warming that we saw. And I'm just showing this over land. If we do the same thing though in CLM, CESM with SLIM, so the idealized land surface model, you see that turning off terrestrial evaporation does lead to less water vapor, brown colors in some places, but not everywhere. It actually leads to a lot more water vapor in many places. And this is because warm air can hold more water and you also get pretty giant cloud feedbacks. So all of this is just to say that clouds can make the response kind of nonlinear, and that's inconvenient and messes with my nice tidy story. But even with these cloud feedbacks, we would expect a really giant continent, so somewhere like Northland, to still be able to dry out the atmosphere in a way that our realistic continental configuration in the present day doesn't really do. So just to wrap that up, we have these competing effects of our local surface energy budget and our water vapor greenhouse. And initially your surface energy budget is going to win, but if you can dry your atmosphere out enough, then you might end up with reducing evaporation actually leading to cooling. So I think I went a minute over and I apologize, but if anyone has any questions, go wild.
Thanks, Marissa. Questions about Northland? It's a fun place to think about visiting. Dave, go ahead.
So have you thought about doing Northland in CSM? Is that, assuming you're not doing that because it would be a hard.
I've thought about it. I've been thinking about it, I feel like, for like 3 or 4 years. I was like, I want to move land around in CESM. And then I went and talked to the Paleoclimate people who work with CESM, and they were like, oh, that's hard. So just getting all the domain files lined up correctly is something I need to sit down and take a couple weeks to do properly and haven't done. So I'd like to, I just haven't because it's harder. It's like literally 3 lines of code in ISCA, so.
Charlie?
Yeah, Marissa, cool talk. So we do have Southland in Antarctica. I guess it's too far south to evaporate. So what's like, is there a critical latitude where you effectively you stop getting evaporation off the land surface?
That's a great question. So I have run these other sort of idealized blob continent simulations, and if you cover the land between 30 south and 30 north, you almost get the full collapse of the water vapor greenhouse that you get from like paving the entire planet. So the tropics seem to matter a lot Whereas putting big land continents in like the extratropics is actually not that big a deal.
Right. I think it's Australia, and I meant to say Antarctica, but yeah, okay.
Yeah.
Okay, thanks.
Yeah, so Antarctica is too far south, too far poleward.
But like 30 degrees is kind of the critical, of it. Okay.
Yeah. So
you
like
have to have a really big
Pangeas
Antarctica.
of the world. Trying to find the stop sharing my screen button. There we go. It's gone.
Great. Well, thanks for your talk. And we have a break now. I'll encourage you to join the CGD seminar. I think Elizabeth just dropped the information for how to join. It's just like the main seminar room, except instead of having lots of people come join our meeting, we can go join a different Zoom meeting if you choose. So the seminar will be from 11 to noon, then a break, and we'll gather back together at 1 Mountain Time to hear from Isla and others. But if folks don't have other questions, I'll see you in a couple hours. Thanks, everyone.
Hi, Will.
Hey.
So this stays open and it stays recording and streaming on YouTube. So
Okay.
I'm not always successful in putting up a screen and then working on my other screen, but I'm going to try to put like a placeholder slide so then people who happen to come across the YouTube feed know what time everything comes back.
Okay, that sounds good. Great.
And then I've been saving the chat since there's so many good resources.
Okay.
And any participant can do that if you want to point that out to them for the afternoon session or for tomorrow. It's in the chat column on the right-hand side where the 3 dots, the horizontal.
The 3 dots. Yeah. Okay.
Hey,
Great.
Elizabeth and Will, I just want to make the point that when you save the chat, all of the chat is saved.
Right.
And so including private chats. So
yep.
Just, fair warning.
Yeah.
Yep.
Okay.
Yep. Thanks. All right. Well, I'll see you. Elizabeth, do you have to go man the seminar also? No.
No.
Get a break.
No,
That's good.
well, it's either help my kids with pre-algebra or close my door and they won't know that I'm not actually on a meeting.
Right.
No.
Well, I hope your math goes well.
Yeah. All right. I'll see you later.
All right. Sounds good. See ya. Elizabeth, do you mind stopping sharing your screen so who is up next? Isla can share hers.
Does it look good?
Yeah. Well, except that it felt like that about a week ago, but now it's like 80 degrees outside.
Yeah. It'll change tomorrow.
You can wait a minute, Isla. We can. It's not quite 1 o'clock, at least by my clock.
Okay.
Maybe I want to give it a minute.
Give a minute for folks to sign on. Yeah. I didn't consider the Zoom log on delay.
Yeah.
Making the schedule.
We have.
Just out of curiosity, can you guys hear my dog snoring really loudly right now?
No.
Yeah, that's good. I was thinking about throwing her out, but she's very comfortable.
Yeah, well, this is the time of day when my dog starts coming in to ask for
want to walk.
Yeah. The standard walk is still many hours away. So yeah.
Time to start asking for it. Avery mostly only asks for food, and that's usually at like 4 in the morning. She's ready to eat, which is a little rough. All right, it looks like we've crossed the magical 40 people threshold. Maybe that's good enough to get started for you, Isla. So thanks for coming back. This is where I wish I could like snap my fingers or clap my hands and get everyone into the seminar room. But instead, we just have to wait for them to come to us, I guess. So our first speaker for the afternoon is Isla Simpson. There's just 4 talks this afternoon and some time for discussion. But Isla is going to talk about changes in surface temperature variability. So go ahead.
All right, thanks. Yeah, so this is work looking at changes in surface temperature variability between CSM1 and CSM2. It's been done with Dave Lawrence, Sean Swenson, Cecile Hannay, Karen McKinnon, and John Truesdale. So just to start, to kind of illustrate the methods here, we're going to be looking at daily average 2-meter temperature, and I'm just showing a time series for 5 years at the location of Toronto. And so we're going to deseasonalize, remove the climatological seasonal cycle that we define as the first 4 harmonics of the seasonally varying climatology. So we'll subtract that out to get anomalies. And then I'm going to focus on the DJF season. So we grab out the winter times. And then I'm also going to remove the winter time seasonal mean, just so that we're looking at subseasonal variability as opposed to any kind of long-term trends or anything like that. So we're going to look at the variance of this quantity. And we'll start by comparing CSM1 with CSM2 in the GOGA or the AMIP type framework. So these are run with prescribed SSTs and sea ice. And there's a 10-member ensemble, and we'll focus on the satellite era record out to when the historical forcings of CMIP6 end. And so this is showing the variance of 2-meter temperature. On the left is CSM1, the middle is CSM2, and then the right is the difference between them. And you see there's been this big decline in surface temperature variance in the wintertime as we've gone from CSM1 to CSM2. And this is for the most part a change for the better. So there's 3 observation-based data sets here, and you can see that CSM1 was really overdoing surface temperature variability. There's some indications, and it kind of depends which observations you're looking at, but maybe in this kind of area of Russia, we now don't have quite enough variability. But overall, it's definitely an improvement compared to what we had before. So what has caused this change in surface temperature variability? Well, we have a couple of possible culprits, the atmosphere model or the land model. And so we've done a bunch of simulations, and Meg talked about these earlier, where you can kind of mix and match atmospheric and land model components. And these are all done within the CSM2 framework with prescribed observed SSTs. One minor detail, but I don't think it really matters, is that VGC is turned off in these runs, which is different from the GOGA runs. So the idea here is we can compare this simulation with this one, where we revert both the atmosphere and the land back to their previous components, just kind of as a sanity check to make sure we can reproduce this change in variability just within the CSM2 code base by reverting those components back. And then we can compare these simulations to see what was the change in going from CLM4 to CLM5, and then these ones to see what was the change in going from CAM5 to CAM6. So here's the overall reduction in variance that we're looking to explain that we saw in the GOGA runs. And then this is the change in variance that we get as a result of the atmosphere and the land components combined. So this is what you get just within the CSM2 framework by comparing CSM2 with a run where you revert both the atmosphere and the land back to what they were before. So we can reproduce that change, perhaps unsurprisingly. Now, this is the influence of CAM, so going from CAM5 to CAM6. And so CAM is playing somewhat of a role. It's particularly important in this region of Alaska, but it's definitely not kind of the dominant factor here. And when you look at the influence of the land model and going from CLM4 to CLM5, you can see that that's producing kind of a hemispheric reduction in surface temperature variability. And we can add up the land and the atmosphere contributions, and they approximately add up to the total. So I've mostly been focusing on why has this change come about as we've gone from CLM4 to CLM5. And so we went through a bunch of different possibilities, all suggestions from Dave and Sean, until we got to the right answer, that it turns out that it's primarily related to the representation of snow density and densification. So this is the difference in variability between a regular CSM2 run and then what I'm calling snow D here, which is a CSM2 run where the snow density and densification settings have been reverted back to what they were before. So what has changed about the snow density? So here I'm just showing the snow fraction for the DJF average, just to show that these are regions that are pretty much covered by snow all the time in the winter. And then in the bottom is showing the DJF average snow density. And so what you see here is that snow is over the land regions is more dense in CLM5 than it was with the old snow setting. So almost a doubling of the density of the snow. So I'm just going to kind of gloss over this because it's not really my area, but these are the nameless parameters we had before, and these are what we have now. And so there's changes have been made to the representation of snow that are all kind of documented in this paper. And I guess probably the important one is what's changed and we haven't pulled this apart yet. We can pull it apart further as to which one is responsible. I just haven't done that yet. But one of the changes is for the density of the fresh snow. And so before in CLM4, it was just a function of temperature. And now in CLM5, there's some added dependence on the wind speed and also this kind of inversion as a function of temperature, so that very cold and windy, you have higher density of snow. And so there's obviously more potential for dense snow in CLM5 here when it lands. And then there's also been a bunch of changes to how the snow the density evolves once it's on the ground. And so it's possible that these are playing a role too. So one question I had was whether we can just worry about the column physics here, or do we need to worry about non-local influences? Like, is the mean temperature changing and that changing the advection of temperature and things like that? And I won't show it here, but the answer is that we can really just think about the local influence. Single column models can reproduce the change in variability if you just give it the change in the land properties and force it with the advection terms and things from a run with CLM5. So to try and understand what's going on here, we're going to look at composites that are conditioned on 2-meter temperature. So we're going to bin DJF days in both of our simulations with the new and the old snow settings according to the 2-meter temperature. So we're grouping days together that have the same 2-meter temperature and looking at how the surface energy balance plays out. And we determine our limits of the bins based on the distribution of our CSM2 with CLM5 simulation, which is the narrower of the distributions. And I'll use 10 temperature bins that correspond to the 0 to 10th, 10 to 20th, and so on, percentiles of the distribution. And I'll just focus on our 3 locations here that are within regions where the variability has changed. So just to get us oriented, I'm just showing here 2-meter temperature conditioned on 2-meter temperature. So both the CLM5 simulation and the old snow settings are shown here. They're just directly one on top of another because we've grouped together days that have the same 2-meter temperature, and that's working pretty well. So we can't see both of them here. So the way to read this is that the cold days are on the left and the warm days are on the right. And so, for example, the second point here is going to be the average of days that have a 2-meter temperature between these values, where these values correspond to the 10th percentile of the CLM5 distribution and the 20th percentile. So we're going to look at the surface energy balance. As Marisa described earlier, it's kind of dominated by these 4 terms. So the shortwave radiation, the long-wave radiation, the sensible heat flux, and the latent heat flux. And we're not going to be in equilibrium here, so you can have an imbalance in these terms. And any imbalance must be accompanied by an energy flux into or out of the ground. So here's our composite of the net flux, and you can see that that's the average of these terms, and that is approximately equal to the ground heat flux, but opposite. So just for one location here with the CLM5 simulation. And so basically what this is showing is that when you have cold days on the left here, you have a net upward flux of energy from the ground to the atmosphere. So that would be a dampening of atmospheric temperature anomalies. And when it's warm, you have a net downward flux of energy from the atmosphere to the ground, which would be also be a dampening of those warm temperature anomalies. So we can look at how has this energy balance changed between the old snow and the new snow settings. And so what you see is pretty systematic. And so as you go from the old snow to the new snow, when it's cold, I mean, when you're kind of at the same temperature at the surface, in those simulations, you have a relatively larger anomalous upward flux of energy from the ground to the atmosphere. So that would be a more effective dampening of atmospheric temperature anomalies. So we can take the difference between the new and the old snow settings, and that's what we get here. So again, you see this is a pretty systematic across these 3 locations. And so then the question is then, why would there be a bigger upward flux of energy from the ground to the atmosphere when it's cold with the new snow settings compared to the old snow settings? So here are just some composites at one of the locations that we're focused on here. This is the bin of the lowest temperatures, and this is the bin with the warmest temperatures. This is not to scale, but you see here the temperature at the lowest atmospheric model level, 2-meter temperature, surface temperature, and then the temperature within the snow layers, and then the soil temperature. So basically what happens is when it gets cold at the surface here, it's not getting as cold in the layers of the snow below. So you have a temperature gradient that is induced across the snow. And as a result, we'd expect an upward flux of energy across, or heat across the snow. And that flux is going to be proportional to the conductance times the gradient of temperature. And that conductance across the snow depends on the density of the snow. And it's in the sense that if you have a higher density of the snow, you have a higher conductance. So here is our snow PDFs of snow density at this location. And you can see that in each of the levels of the snow, the density has increased. And so ultimately the model's calculating this flux at each of the individual snow levels, but what if we just kind of approximate it as a constant flux layer and just say we have an average flux across the snow that's given by the average conductance times the temperature difference between the uppermost level of the, or the temperature gradient between the uppermost level of the snow and then the soil below. So if we go back to our surface energy balance composites, and the question is, can we explain this difference in the surface, the flux from the ground to the atmosphere, because we have a larger flux of energy across the snow? And what I'm showing in green here is that kind of diagnosis of the change in the flux of energy across the snow that's given by the conductance times that temperature gradient across the snow layers. And you can see that that matches really well the change in the upward flux of energy that we have between the new snow and the old snow settings. And all of that change is coming in from the change in the conductance. So if we just recalculate this, but use kind of the mean conductance from CLM5, then you don't reproduce that change. So the conclusions here are that there's been a big reduction in surface temperature variance going from CSM1 to CSM2, and this is, for the most part, it's an improvement. And really a large contribution to this has come from the changes in going from CLM4 to CLM5. And the relevant change is the representation of snow density and densification, and ultimately the fact that the snow has become more dense. So when it's more dense, you have a higher conductance, and that will give you a larger anomalous flux of heat across the snow layer when it gets cold or when it gets warm. And that results in a more effective dampening of atmospheric temperature anomalies to reduce the variance. So there are a number of ongoing work things still to do to tie this up, but I'll just leave that there and take any questions if there's time.
Thanks, Isla. That's great. Time for a quick question or two to Isla. Keith.
Isla, it's a nice analysis. Now that you've got to the conclusion, have you looked back at land-only simulations that are the way that the land development typically happens? And do you see this result in the sorts of analyses that they might have done when they were doing this model development?
Yeah, that's a good question. I did look at land-only simulations, but way back, and but I think, yeah, I would imagine that you could look at the surface energy balance changes and see them, but not the surface temperature variability changes, because I think they would be very constrained by the forcing. But that's a good idea to have a look.
Yeah, I'll second that. It'd be really nice, this is Dave, to figure that out, because then if we do find that we can diagnose it in land-only simulations, that means then we could then assess this through the PPE, easily, and see what, adjust the sensitivity to the various snow parameters which are in the PPE and get a better sense of this, and also make sure going forward that we don't lose it as this benefit.
You?
Yeah. Hi. I'm just wondering because you are using like AMIPS type simulations, which using the prescribed sea surface temperature and sea ice. So I have, based on my previous experience, that for example, like the winter temperature variability in high latitude could be significantly influenced by like some high pressure system during the winter. But this AMIP type simulation, I think that they have like their incapability to reasonably simulate some variability in the winter, so which will produce a very poor performance of the temperature variability. But for your study is not the case, because it's a comparison between the different snow scheme. But this could be a potential problem if you want to try to compare this with the reanalysis data. Yeah, thank you.
Right. Well, I did start out by looking at the coupled simulations, and the temperature variability in the coupled simulations looks pretty much the same as in these AMIP simulations. I didn't show it because it was with the large ensemble that the data is not really available to be shown yet, but it looks pretty much identical. The conclusions don't change if you have a coupled ocean and sea ice.
Okay, thanks.
Great, thanks, Isla.
Thanks.
And Lucas, do you want to start sharing your screen? Yep, so our next speaker will be Lucas Vargas Zapatillo. I don't know if I'm saying that right.
Close enough.
You can introduce yourself and help us all with their pronunciation. Go ahead.
Yeah, thanks. Hi, everybody. I'm Lucas Vargas Zapatello. It's great that to be here. It's going to be fun to follow up with Isla. We're going to move from winter to summertime. And instead of talking about differences between models, I'm going to talk about changes in models as the mean climate warms. So trying to explain why summertime temperature variance increases as the mean state climate warms. And this is work that I've been doing out at the University of Washington with David Battisti and Marcia Baker. Oops. Okay, great. So first things first, just a quick primer on temperature variance. If you think about a probability density function of temperature with cold temperatures on the left-hand side and warm temperatures on the right-hand side, the variance is just one way of characterizing the sort of breadth of this distribution. So really understanding what the sort of natural envelope of possible temperatures is to a particular land surface. There's other ways to do this too. You can look at skewness. I've been thinking about this as well, which takes into account the shape of the distribution. Variance is neutral to that shape. You wouldn't be able to tell if a distribution or density was skewed positively or negatively just by thinking about the variance. I'm happy to talk to folks offline about that. First things first, I'm going to skip a lot of stuff here. So we're going to derive an equation for temperature variance over the land surface, but I'm going to skip almost all of it. If you're more interested, this is the paper where we really kind of dive into a lot of this stuff. And I'm also happy to give me a shout. I'm easy to reach and have lots of free time. So definitely let me know if you want to talk about this more. But skipping straight to the equation, on the left-hand side here, this is our notation for temperature variance. And first things first, it's going to be a function of three different forcings, or what we call forcings. The first of these is the variance in solar radiation that is seen by the land surface. So this is a map of that quantity obtained from the Ceres satellite for 18 years of the historical period. The second forcing on the model is going to be the variance in precipitation here. So I'm plotting this in energy units here, but it's just the latent heat of vaporization multiplied by the variance in precip across the land surface. So again, this is all from observations. You can see in the dry western parts of the United States, this variance tends to be pretty low. And as you move towards the east, where in summertime it rains quite a bit, the variance tends to go up quite a bit. This is also all on monthly timescales, I should mention before we get too far into this. The last model forcing that we're going to think about is covariance. I'm not plotting it here. The map of it just sort of looks like a smushing together of the two maps I'm showing here. The other important thing to remember is that that covariance term is negative everywhere because shortwave radiation and precipitation are anti-correlated on monthly timescales. So those are the model forcings. Now I'm going to talk about these two parameters that are sort of very impactful, particularly when we think about changes in the future climate. So the first one of these is zeta. We're going to call this the dryness index. It's a value of 0 and 1 that sort of designates what's the overall aridity of the land surface. So this goes from 1 in the far west, where the soil is quite dry and the temperature is very warm, to closer to 0 as you move towards the east coast of the US. The second big parameter that's quite important is this gamma here, which we're going to call the moist sensitivity. Again, this is sort of the inverse of the dryness index. It gets larger when available soil moisture is quite high, which acts to damp the overall temperature variability. So these parameterizations fall out of the way we characterize the land surface fluxes. And the really important thing to remember about both of them is that they are functions of the mean state temperature and soil moisture. And this will be really important later, because when we change the mean state to predict where temperature variance is going further, we're going to rely on the way that these two parameters depend on temperature in the current climate and where that will go in the future. So how does this model compare to the observations? I'm showing here the variance ratio of the temperature variance during summertime predicted by that diagnostic equation to the temperature variance in the observations. So places that are red, the model is over predicting temperature variance. Places that are blue, the model is under predicting temperature variance. We'd obviously like this ratio to be unity everywhere, or a value of 1. There's obviously some errors here. I can talk about those if people are really interested. There are some pretty good, physical reasons why our parameterizations aren't adequate to describe the land surface fluxes everywhere all at once with minimal tuning. But overall, we find pretty good agreement across North America, which is obviously the sort of original study domain here. This is just a probability density of the value of this ratio everywhere that's plotted on this map. And then once we got done with that, we extended it to the entire mid-latitudes. That's the plot for this one. So we can see that even though we sort of focused our attention on North America initially, applying this model to the entire mid-latitudes resulted in a pretty similar distribution that was centered on unity. So that's really nice to see. There's also a plot of this for the Southern Hemisphere during summertime that looks almost identical. So that was really nice to see. So now we're going to talk about CMIP6 temperature variance changes within the CMIP6 ensemble. So what I'm showing here is the absolute temperature variance increase during summertime in the CMIP6 at the end of the SSP 585 simulations. And the stippling here is showing regions where more than 75% agree of the models I analyzed here agree on the sign of the change. So we can see that almost everywhere, summertime temperature variance increases dramatically by the end of the 21st century in this sort of worst case climate change scenario. And these are really big increases. So most of the places experience a 30 to 50% increase in temperature variance on almost every major continental interior. So we'd like to go after this a little bit and try to use our model to understand where these changes are coming from. And the first way we're going to go about doing that is just taking a derivative. So I mentioned earlier that the parameters used in that diagnostic model for summertime temperature variance are functions of the mean state climatology. So what that means for us is that we could take a derivative with respect to the mean temperature and derive a sensitivity value of summertime temperature variance to the overall mean temperature everywhere in space. And so we're going to do that exercise and then multiply what we get by the local temperature change everywhere in the model to obtain the absolute temperature variance predicted by the diagnostic equation. And then we're going to compare that to the change we see in the climate model ensemble. So again, on the left-hand side here, I'm showing the SSP 585 multi-model mean increase in summertime temperature variance at the end of the 21st century. And now on the right-hand side here, I'm showing the diagnostic model projection solely using the local mean temperature change everywhere across the land surface. So the agreement between these two very different approaches is really nice to see. So we can see here that the diagnostic equation predicts both the magnitude and the spatial pattern of the changes in temperature variance from climate model simulations. There are a few under predictions in the few places, but overall, the agreement here is really nice to see. And the spatial pattern, again, is pretty accurate. And again, all we're doing here is using the sensitivity of that temperature variance equation and the change in local mean temperature to back this up. So there are a lot of processes that we're not considering here. I can talk about that more if folks are interested. This is only the change that you would expect given the fact that mean temperature increases across the land surface. So just a quick intro here about what the mechanism is. So why is this happening, in other words? And it's really important to think about this last term here. So again, we saw that the precipitation variance is multiplied by this dryness index, which again is zeta here. But as the mean state climate warms, like I said, that parameter is sensitive to the mean state temperature. And as you warm due to climate change, that parameter is going to go from less or closer to 0 to closer to 1 and act to amplify the precipitation variance that the land surface is seeing. So when you look at just that component of the temperature variance increases, you get most of the answer just by amplification of the precipitation forcing via overall surface aridification due to climate change. And I call this the sort of warming amplifier that, the music can stay the same, but by turning up the mean temperature, you're really amplifying the resultant variance associated with the precipitation forcing that the land surface sees. So just wrapping up here, what have we learned? A simple model of the land surface energy and moisture budgets can reproduce the observed pattern of temperature variance in reanalysis, observations, and climate models. And there's not too many tunable parameters in here. Again, most of those parameters emerge sort of naturally from our characterization of the surface energy fluxes. The model is sensitive to mean state temperature and relative humidity, like I said, so changes in these variables can be used to predict how temperature variance will change as the mean climate warms. Summertime temperature variance is increasing due to climate change, according to the CMIP6 ensemble, and the multi-model mean signal is driven apparently almost entirely by the warming impacts on relative humidity and surface aridity. And these changes are, obviously significant. We've already talked about how they're pretty big relative to the baseline pattern of temperature variance. And definitely contribute to risk for vulnerable communities and agriculture. So I'll leave it there if we have some time for questions.
Great, thank you, Lucas. Any questions?
Go ahead, Katie.
Thanks, Lucas. That was a really interesting talk. I guess to your first point on your final slide about this nice agreement that you found, what are some possible applications that you see for this sort of simpler framework going forward?
Yeah, so one of the things that I think is really sort of easy to do with this is you can take, I was using forcings from observations for all of those agreement plots, and basically everything I did in this talk was all derived from observations, but you can do it for climate models as well. And so I think this is a really nice way to, one thing I didn't mention was that a lot of climate models have very large biases in summertime temperature variance. So those biases that Isla showed a little bit ago are not just limited to wintertime. And so one of the nice things about this model is you can sort of use it to unpack what are the sources of those biases without, doing these, various simulations. So in other words, one of the things we've done with this is, I forget which model we did it for, it wasn't CESM, but by splitting up those components into, a forcing, or is it your mean state soil moisture that's too low, we were able to see that in one model, for example, the radiative forcing that the surfaces was just like totally out to lunch. It was like 3 times the size of the observations. And in that particular model, that seemed to be what was responsible for their excess temperature variance biases, versus in another model, it could be that the land surface is overall too dry or the precip was out to lunch. So it's a nice way to sort of see where the sources of biases are coming from.
Very cool, thanks.
Hey, Will, can I ask a quick question? Do we have time?
Yeah.
So Lucas, that was really nice. It was really clear. I appreciated that. And but you said this was with monthly analytics. Can you comment on how it would change if you'd used daily data?
Yeah, sure. So I'm working on this currently, and the main issue with using this kind of diagnostic to get at daily variability is really that the way precip works on daily timescale cannot really be adjusted to fit within this framework. You need a more dynamic representation of soil moisture variability if you're going to get to daily data. The other thing, obviously, I'm just doing this all in a column approach. So as far as like temperature advection goes, we're not considering any of that, which is, I think, some of the reason for those biases in the high latitudes. But to your point, so for example, you can, because radiation is just sort of fluctuating around a mean value on daily timescales, it's reasonable to use that part of that equation to isolate the radiation contribution to daily temperature variance. But it's when you get towards the precipitation that you need a more, not a more complicated model necessarily, but a model that actually resolves soil moisture rather than just looking at these fluctuations on monthly timescales. Does that answer your question?
Yeah, thank
you.
You.
Cool. Yeah.
Great, thanks, Lucas. Charlie, do you want to go ahead and share your screen? And our next speaker is Charlie Coven from LBL, talking about the long time scale simulations that we've done.
Yeah, can everybody see and hear everything?
Yep.
Okay, yeah. So I'm going to like drop the frequency by several orders of magnitude from short-term or relatively short-term fluctuations to the longest-term fluctuations as we run the models past the sort of normal horizon that we tend to stop of 2100 and look at what happens on some of these extension scenarios out to SSP or out to 2300. And the framework that I want to start off with is this idea of the linearity of global warming to cumulative emissions, right? So this is like kind of the main the main change in climate modeling over the past, or in the use of Earth system models over the past decade is this idea that because we have these compensating effects whereby each incremental bit of CO2 radiative forcing with increasing CO2 tends to weaken because of the logarithmic forcing of CO2 on climate. That gets balanced out by the fact that the carbon cycle feedbacks tend to strengthen with each increment of emissions because the carbon concentration feedbacks weaken and the carbon climate feedbacks strengthen. And so those two effects kind of balance each other out. And so you end up getting a roughly linear response to the global temperature anomaly to total cumulative emissions. And then, this is the basis for all the stuff that we do in terms of climate policy, such as, there being a finite carbon budget for a given temperature target and things like that. And then so Damon Matthews led this nice review article in Nature earlier this year, or one of the Natures this year, I think it was Nature Geoscience, looking at basically what are the possible ways that we might see deviations from the linearity, and sort of propose a bunch of possible ways that could either change the slope of this relationship between temperature and cumulative emissions, and also possibly some ways that it might deviate from linearity. And so what we want to do in these long-term simulations is ask, do any of these things show up or not? And so the three scenarios I want to talk about are really sort of bracket the range of possibilities. So there's a super high-end SP585 out of 2300, and then sort of two lower ends, one in which we sort of mitigate later and have to mitigate stronger in order to end up in the same sort of mitigated climate. So those two are the SP534 overshoot, which diverges from the SP585 in the middle of the century, goes into really strong negative emissions, and then ends up in the stabilized climate, or stabilized CO2 concentration, versus the SP126, which is stabilized earlier and sort of relaxed towards the climate. And so what you see so that's on the left-hand side of the CO2 trajectories. On the right-hand side are 5 or 4 Earth system models, and then one reduced Earth system model of intermediate complexity that have done these scenarios out to 2300. And so, basically what you see is, the global temperature kind of responds in the way you'd expect to CO2, that under the high emissions, you get a very large amount of warming. And then under these two more mitigated ones, you get, either peak in warming and then reduction, or sort of a lower peak and stabilization. And so I want to dive into a bit more detail on what's going on in some of these simulations. Particularly, so I want to start off on the carbon cycle stuff. So on the left-hand side are the inferred fossil fuel emissions from each of these runs for each of the ESMs. So these were run with specified concentrations, and so you can figure out the change in atmospheric carbon as well as change in biospheric and ocean to figure out what the emissions must have been that were compatible with that. And then on the right are the net long-term land and ocean sinks. And a few things sort of pop out immediately. One is that, particularly in the ocean, the sinks are really strongly just following the emissions. That, after the peak in emissions, the peak in the ocean sink drops under the high emissions, under the strong overshoot scenario, where there's strong negative emissions, you get a strong negative sink in the ocean because the ocean basically outgasses carbon to resist those negative CO2 emissions. And then under the SP126, the sort of early mitigation without as strong an overshoot, you basically get a relaxation. On the land, the story is a bit more complicated. In most of these cases, you get this transition from a sink to a source under both the high and the overshoot scenario, but for really different reasons. Under the and I'll get into those reasons actually in a bit, but also that the ocean, that the land models, there's not this sort of consistent thing. Like there's kind of just a lot of different trajectories that these different land models are showing, and the pattern isn't quite so clear. Although there is an indication, particularly in the SP534 overshoot scenario, the one with the strong negative emissions, that the terrestrial biosphere also acts as a source of carbon, basically resisting those negative CO2 emissions through basically a negative, effectively a negative CO2 fertilization effect that happens under declining CO2. So now I want to get to these cumulative emissions plots, like I showed in my original slide. And so there's a few things here. One is that this linearity paradigm, it mostly holds, right? So on the upper left here, under the SP 585 out to going out to about 5,000 petagrams of carbon, which is just an enormous amount of CO2 emissions, the linearity roughly holds. At the end, some of the models show this sort of continued warming even after emissions stop, but for the most part, it's sort of amazingly linear on this. So that's good in terms of this idea of the cumulative emissions value. In the middle, and I've colored each of these by century because particularly in these overshoot scenarios, things don't move sort of monotonically from left to right. They move from left to right, and then under negative emissions, they then start to move back from right to left as the scenario sort of forces the negative emissions. And the key thing here is that, again, most of the models are linear, but then one of them does this weird thing, which is it sort of peaks upwards at the end. And so even though there's no extra emissions, you get this additional increment of warming. And I'll come back to that in a bit. And then in the SP126, again, it's roughly this sort of linearity. And then as things kind of relax, then you basically get this kind of some degree of committed warming or cooling that happens. But again, the linearity is roughly there because the dynamic range in the SP126 is much smaller. The variability ends up dominating a bit more. So okay, linearity mostly holds, but I want to come back to this one case where the linearity doesn't seem to hold and ask what seems to be going on there. And so that's CESM2, conveniently enough for this group. And what seems to be going on here is, so if you look at the spatial pattern associated with this 23rd century warming in CESM2 under the overshoot scenario, that's what I'm showing in the upper right here. And basically you get this peak in warming over the North Atlantic and then over this sort of Arctic region. And so that's it. Okay, well maybe there's something going on with the AMOC in this scenario, that there's that basically under this scenario, because it's sort of this peak and overshoot and then recovery, the AMOC kind of goes, the collapse, and then it recovers. At least in CESM2. And so interestingly, it's the only one of these models that has this really strong AMOC recovery under this scenario. And it also seems to be the one model with a strong amount of warming. And so it's consistent with this idea that basically AMOC collapse provides this sort of transient buffer of cooling to counteract warming. But then if you allow AMOC to recover, then some of this committed warming starts to resurface again. Interestingly, the model doesn't seem to do that in SP126. You don't get this extra amount of warming. So you end up actually in a higher, a warmer planet under the overshoot scenario in the long term, after this sort of AMOCs had this ability to recover, than in the sort of gradual and earlier mitigation scenario. And so I don't think we fully understand that exactly what's going on here, but it's also consistent with a paper by Esui Hu earlier this year who showed that between the E3SM and CESM, they both have very high equilibrium sensitivities, but CESM's transient sensitivity is lower, partially because of this AMOC kind of buffering the warming effect. Okay, so now I want to focus a bit more again on the carbon cycle and getting particularly for this audience, what actually is going on in the carbon cycle in these models. And I guess I want to make the point that the terrestrial carbon cycle of these models isn't just that the spread of these global integral values is kind of all over the place, but qualitatively they're all telling completely different stories that have almost nothing to do with each other. Some models have strong sinks in the tropics that become sources. Others happen to high latitude. Some models have a strong permafrost carbon feedback effect, or in the case of the UVic ESM, or a weak permafrost carbon feedback effect in the case of CESM2, et cetera, et cetera. Like these and I think that this probably comes as not a great surprise to those of us working in the terrestrial carbon cycle, that the models are all over the place. But it's not just that they're all over the place in terms of the sort of plume spread, and they're telling relatively qualitatively consistent story. When you actually dive into the details on the spatial patterns, it's kind of even worse, particularly under the high end emissions. Under the overshoot scenario, there's a bit more of a qualitative consistency. And I want to compare that to the ocean models, where, in some cases, actually, the plume spread is quite wide for on the SP585 after 2100. The global integrals, on those model spreads is, it widens quite a bit, but nonetheless, the models are all telling the exact same basic qualitative story about where the carbon is going, and thus kind of why, even if the magnitudes might differ. And so I think that, for the land cycle, terrestrial carbon cycle, it's always really I find it really disconcerting to look at this because, here are a bunch of models that are all really state of the art and telling completely different stories, versus the ocean cycle, where, they're basically all telling different versions of the same story. The more you sort of dig into it, the worse it gets, right? So if you separate out changes to the vegetation versus changes to the soil, again, some of the models have loss of vegetation in low latitudes versus gain in high latitudes, others don't. Again, particularly under the high emission scenario. And then if you look at the soil, some of the models are losing a ton of soil in the tropics, some are losing it in high latitudes. Just like, basic qualitative dynamics are all really different between these models. And, again, we all kind of know this, that the terrestrial carbon cycle is all over the place, but I think it really speaks to the need to come to, a better agreement on what we think might be going on in these models. And particularly this is obviously a tough case, right? Looking at these models after this century, when we would expect things to break down, or we might expect things to break down. And here we can see very clearly that any qualitative agreement that exists in the short term breaks down completely under on the longer term. Okay, so I'll just end there. What do we learn from all this? One is, the linearity of the sort of temperature as a function of cumulative emissions paradigm that mostly holds through a remarkably wide range of emissions. There's this possible wild card that CESM2 seems to be throwing under the overshoot, in which what appears to be driven by AMOC, which sort of mitigates warming during the AMOC collapse phase, but then exacerbates it during a possible AMOC recovery phase, could lead to this pretty strong nonlinearity in the TCE relationship. We can expect some sink to source transitions, either in strong overshoot scenarios for both land and ocean, or possibly under high emission scenarios on land, but for really different reasons. In one case where it's basically a negative carbon concentration feedback, or negative CO2 fertilization on land, that leads to sort of outgassing from both land and ocean, whereas in the high emissions case, it's basically a strengthening of the carbon cycle the carbon climate feedbacks, which then overwhelm the carbon concentration feedbacks. And then, just this just persistently depressing story on the land cycle that, the harder you look at the land cycle, the worse things get. The models disagree in just about every possible way. Which zonal bands are most active? What are the signs and strengths of the vegetation versus the soil response within any zonal band? The timing and the century-to-century continuity of the patterns. In the ocean cycle, the carbon cycle, the models are all telling qualitatively the same story in terms of the basic geographical and temporal patterns of the carbon fluxes, even into the cases where the ensemble spread widens considerably after 2100. And I'll end there.
Awesome. Thanks, Charlie. Maybe in the interest of time, is it all right if we come back for questions after?
Yeah, sorry for going over.
No, it's great. It's cool stuff. There's a couple, Charlie, there's a couple of questions for you in the chat. Maybe you can answer those there.
Sure.
Yichi, if you want to share your screen. So our last speaker for today is Yichi Luo from NAU. We lost your screen.
I have trouble to. So can you see my screen?
Yep. There you go. Well, that's great.
Charlie's talk actually provided great prelude for my talk, and he emphasized the uncertainties among the land models, and he emphasized all those models involve his long-term studies and cannot agree on any, almost any aspect. Actually, today I'm going to talk about uncertainty analysis of land carbon cycle prediction, and I slightly changed the title to a matrix approach. So, as probably some of you already know that we have converted a CLM5 biogeochemical cycle module into matrix equations. And we use 4 matrix equations to represent the CLM biogeochemical cycles. And those 4 equations including vegetation carbon cycle, vegetation nitrogen cycle, soil carbon cycle, and the soil nitrogen cycle. And actually we have converted about nearly 20 models into matrix equation in the unified form. Basically, this equation in the middle of the the slides, all the models eventually come down to these relatively simple matrix equations. And with the matrix equations, and we gain a few advantages, such as simplicity in the model structure, high modularity in code, clarity in diagnostics, and the computational efficiency in spin-up. And Dave's talk already mentioned that that now he can run 120 loops to get the equilibrium. That's about nearly 20 times more efficient than the AD method. And Cai-Jun Liao on the Thursday morning going to talk about the spin-up. And today I'm going to focus on the clarity in diagnostics. As Charlie's talk mentioned that the uncertainty prevails in all the land carbon cycle modeling. And this uncertainty issue has motivated the community to do research in many aspects in the past 15 years. So the the model-to-model differences occurred in the 3rd IPCC assessment when the carbon cycle was the first time incorporate IPCC assessment. It appeared in the C4 MIP. These figures has been used probably by thousands of times to motivate our studies. And in the IPCC AR5 and also in CMIP 6. So basically the model uncertainty generated when we use a different model to generate the output, and then output, the model output differs quite a lot. And so actually, no matter how different the model structure are, and actually all those models simulate how much carbon get into the system, and then carbon cycles within the different pools, which the cycling within the pool usually measured by residence time. So many of you in this meeting has made great contributions to understand the uncertainties. In general, the uncertainty is caused by 3 sources: the variations of forcing, variations in carbon input, and the variations residence time. Actually, strictly speaking, variations in forcing all influence the variations in MPP and the residence time. So strictly speaking, we only have 2 sources of uncertainties. And Enqing going to give a talk in Thursday afternoon, and he used the matrix approach to understand the uncertainty. Basically, he used the 8 models with a very diverse model structure, and such as a team with two pools, and OCD has 100 pools, and the CLM 4.5 and the OCD has multi-layers soil, multi-layers. Other models only have 1 layers. So what Enqing did is actually many of the matrix model came from the training course, and those trainees brought their own models and converted the model to matrix equation. and Enchain kind of put them in the uniform and expressed those models in the matrix equations. And as you might expect it, that's when we use 8 models to simulate carbon dynamics, and then we see these model-to-model differences exist. What Enchain did is we try to standardize all those coefficients in that matrix equation in A, C, K, and B. Once we standardize, actually we can get identical output. So that means whether you are using TIM with a 2-pool model or use OCD with 100 pool models, or the CLM with 70 pool models. And as long as those coefficients are standardized, we can generate identical results. So what did we learn from Enchain's study? And his study, certainly he's going to explain the more technical details during in his talk. Probably you can get more descriptions about his study. But overall, his study indicate model structure does not matter for projecting carbon dynamic. I understand this conclusion might stun you or might upset you, because many of you made a great contribution to develop a different model structure. Certainly, developing more different model structure, it's not, it's in many cases essential to represent different biological and geochemical processes. But in terms of projecting carbon dynamic, that's not a fundamental property. Fundamental property to determine the carbon trajectory is a resonance time. And certainly in his study, we kind of fixed the carbon input. So in the general system, supposed to be resonance time and the carbon input, those are determined. So our study is not about eliminating model-to-model differences. And hold on. And what we try to illustrate is a matrix approach, make model uncertainty a tractable and completely transparent issues. Basically, we offer an analytical framework to understand and quantify model uncertainty. So I'll kind of expand the last point about this framework. NCAR has been leading the model development, played a leading role in the model development. And so NCAR's model has been involved in many of those MIPS. And as far as I can get the information, for C4 MIP, and NCAR at that time used the so-called climate system model 1.4 to simulate. And based on my reading, there's the NCAR's model predicted in middle of pack. And then add NCAR's model adding nitrogen process for the CLM 4.0, and then the carbon become lowest among the C4 MIP. And then from CLM 4.0 to the CLM 4.5, adding vertical profile, and then the carbon become the highest. I understand some of the simulation, probably NCAR's model in the middle pack, but for this particular analysis, it seems like CESM is very high, and Norway's Earth system model also using CLM version, it's become very high. So in the modeling world, it all makes sense. Carbon is cycling faster when nitrogen processes are incorporated, but slower when the vertical profile added. What about in the real world? would that happen in the real world? And basically, we ask the question in another way. Would the carbon process in the real world change with a different process being modeled? I think this is a serious question, is that right? So if we really want to understand the question, we need to understand the model structure, parameterization, and the predictions. So we used the data sets from a warming experiment conducted in Tibet Plateau by Suli News Group from Chinese Academy of Science. Her graduate student and Song Wang and used the data assimilation, assimilated the data to two models, model structures. And basically so-called structure 1, structure 2. Structure 1 is a carbon-only model. And structure 2 is basically coupled carbon and nitrogen model. And then he got the two sets of parameters. And you can see that even the same data set, but when we use different model structures, and then we estimate the parameter for carbon-related parameter actually shift. And you can see that use the CN coupled model, get the parameter actually in many of them it's larger, but some of the cases is smaller. And then we use those parameter and feed back to original models and do prediction. Actually, even the model structure is different, but the prediction is similar. So basically, that's use the different model structure generate different parameters. So when we use two model structure to estimate the two sets of parameters, we generate similar predictions. Then let's ask another question, that when we use the same data set to train the model, get estimated the parameter, and then we change the model structure. And then we use the original model parameter and to do prediction. And then we generate different predictions. So that's basically when we change the model structure without corresponding change in parameters, we generate a different prediction. And similarly, and the CLM 4.5 and 5 adding the vertical profile, this is very, very important to understand the carbon dynamic at the different depths and ecologically essential. And then actually when we compare the observed data, the default CLM 5 and actually way overestimate the deep soil. And the Fong Tao, and he going to give a talk also on Thursday morning and talked about his study with the so-called PRODA approach. PRODA approach is the process guided deep learning and the data assimilation, data-driven modeling, and then basically that showed that how we can use the big data to constrain parameter. So we try to use those examples to make a point that the reparameterization is required when the model structure is modified in order to reflect the real world. And so basically the summary of my talk is matrix approach make the uncertainty analysis a completely transparent and a tractable issue. When we change model structure, parameter value need to change accordingly. Otherwise, the model project different trajectories for carbon dynamic. Reparameterization become essential each time after model structure is modified. And we have developed a PRODA, it's an approach that combines big data and data assimilation, machine learning with a complex model. So make it possible to do reparameterization much faster. And I'll also take the opportunity to do announcement, and we are still accepting applications for force training course. And the deadline is March 15th. And if you are interested in, and you can go to my lab webpage or send email to me or Li Fen Jiang. And we, in the past, we have the, 2018, we had in-person mini symposium plus training course, and 2019 was in person, but last year was a virtual one. Thank you very much. A couple more.
So we have half an hour for discussion now, and maybe we'll start with questions for either Charlie or Jackie. I'm sorry, Charlie or Yichi, or Jackie, if you want to ask Jackie any questions. So Yichi, I'm a little surprised that you can say that model structure doesn't matter, and then in your next slide you said it does matter because it changes the parameter values.
Well, the model structure in the sense that model structure matters only when it affects the resonance time. If we, the 2-pole model with 10 versus 100 model with OCD, and we can get identical trajectory if the resonance time has been standardized.
Gordon, go ahead.
Okay, this is for Charlie. Charlie, I'd like to get your thoughts, on the spread or the differences between the land carbon cycle and the ocean carbon cycle. I've always sort of interpreted as, well, maybe the ocean carbon cycle is more driven by ocean circulation. It's more sort of physically based. There's a longer history then of ocean general circulation models relative to land models. Do you think that's, and then the answer would be that, well, the biology is really important on the land and the biology is really messy compared to sort of the fluid dynamics that you might see more dominating on the ocean side. Do you think that's the right way of explaining it, or do you think there's more going on in terms of why the ocean models have sort of lesser spread than the land models?
I think I guess my interpretation is that's part of it, and then in addition, I think there's also, the ocean has a longer history of these kind of canonical data sets, like, going back to Takahashi, and everybody sort of knows what the atmosphere ocean, CO2 gradient looks like. There might be errors in that, but everybody has at least been using the target. Whereas on the land side, I feel like there haven't, the targets haven't been as obvious. There've been things like NDVI, which is observable until recently, and now we're starting to build better targets for at least things like biomass or SIF or things like that. But so I think it's everything you said plus just the availability of big canonical data sets.
Dave?
Maybe I'll let Keith go, but he's going to respond to that.
Sure, go ahead, Keith.
Sure, thanks. Another factor that comes to mind differentiating on those timescales between the ocean and the land is that a lot of the timescales in the ocean are longer. And so if you looked at a timescale of like how the ocean models respond over 1,000 years to a pulse of carbon, you might see more divergence because you're hitting more of the circulation patterns of the ocean as opposed to the centennial decadal or centennial timescales. And the sort of the timescales inherent in the terrestrial response are, I think, fundamentally shorter than the near surface timescales of the ocean. So I think that the timescales of the components is also contributing to the greater divergence in the land model than you see in the ocean.
Dave, did you want to make your point,
No,
or should we switch over to Renato?
Yeah, switch.
Okay. Renato.
Hi there. Thanks for your talk, Charlie. My question is more related to the fact that you're expanding the runs up until 2300. And I understand why we would do that up until, the end of this century. But what is the real point of like extending 270 years in these runs, given that the uncertainty, the natural uncertainty of the model is probably already very, very large by the end of this century. So first off, I like the way you show like a Hofmöller plot with time going on, so we can really see how these Earth system models disagree in terms of land uptake. But my question is why we need to go that far away? And second, does the spread of these model results increases after 2100, or they pretty much agree up until the end of the century, but then they start to get messy after that?
Yeah, thanks, Renato. I guess I have a couple of responses. One is, I think that this idea of like 2100 is like a permanent fixed end of our planning horizon, gets like, that strikes me as like a bit of, there's a social construct there that, originally, like, in the 1980s, 1990s, when people were designing scenarios, that kind of made sense. But, it's 30 years later, and we're still ending our scenarios 2100. Present, at least our definition of present has been moving forward. But I think our definition of like what our planning horizon should also be, at least the same rate, right? I mean, kids being born today we can expect, hopefully to live to 2100, and so it's not a sci-fi time horizon. Maybe 2300 is, but I think it makes sense to ask some of these questions, particularly, and I think particularly as we start to explore some of these scenarios that go beyond sort of a monotonic increase of CO2. As we start to explore, some of the questions of like, does it matter, if we start mitigating now versus if we start mitigating, more heavily in 30 or 40 years, like, what's the difference in that? And those differences only show up, or start to show up really strongly after 2100. So I do think it makes sense to ask these questions. And if our Earth system model, if we want to make the case that Earth system models are useful tools for policy relevant questions, there is a set of policy relevant questions that have to do with timescales after 2100. Again, maybe not 2300, but I still think it's, I think one of the nice things is that there's a convergence of, because of supercomputers getting faster, we can do things with our system models now that 10 years ago you can only do with an EMIC. And so I also think it makes sense to, because so much of the long time scale literature is written with EMICs in general, and specifically actually with the UVic ESEM, because I think that's been the most widely used EMIC for a lot of these things. I think it's useful to bring in full complexity ESMs and say, like, what are we missing by only relying on EMICs for these longer time scale questions? And I think, like, this weird thing with AMOC is kind of an example of like, oh, nobody was expecting that, or at least nobody I've talked to was. So yeah, I mean, I hear your point, right? That we're, it's hard enough to know what the models are going to do in 30 years. Why should we ask them what they're going to do in 300? On the other hand, they're tools, and we want to exercise our tools and go out to these longer things. So I don't know.
Dave, go ahead.
Yeah, so I got a few things. One, I am wondering about this discussion about the ocean, why the ocean is showing more consistency, and I guess neither Keith's nor Gordon's answer resonates with me. I think they both thought about it more, but I'm not sure the ocean has that much more experience than the land in terms of model development, and the biogeochemistry development doesn't seem like it's any longer than the land, unless I'm missing something. Whether the oceans are better models. So anyway, and then Keith's about timescales, maybe one thing, but that still doesn't quite explain why there isn't like this diversity across the ocean models in terms of where that uptake is. And so it feels like there must be just a more physical process that's sort of lending to some more uniformity in the ocean models. It's just easier, right? And that maybe that's the land CO2, sorry, the ocean CO2 flux is just more controlled by solubility or something like that. So I'd be curious about their comment. And then the second question is really to Yichi and Charlie, and that's like, what if we do have this, intense disagreement across models? What do we, we've been trying to resolve for forever. What's the strategy to try to make progress?
Charlie, go ahead.
No, you go first, Yichi.
Well, one of the things we could do is, if Charlie's experiment has an output, especially the pool, each of the pool output, we can reconstruct the so-called aftermath matrix model, like the what's his guy did the use this ELM model output and reconstruct the matrix model. Then we can apply the matrix approach to understand why model varies so much. We can identify the causes.
Yeah, I guess I'd agree that's one strategy. I think I think your statement that model structure doesn't matter except in as much as it governs turnover times, residence times. I don't totally agree with that. I think that it matters in other ways. Although, sure, most, in general, most things can, at least in the carbon cycle, can be framed in terms of either productivity or turnover time. But, like Adriana was asking in chat, is there fire? Is there dynamic vegetation? Is there permafrost, things like that? Traditionally, I think when we talk about models, like you say, Yichi, we've been sort of fixated on, how many soil pools does it have and this kind of thing, and that really misses a lot of the important questions, which are, what does the distribution of turnover times look like? What is the sensitivity of turnover times to climate, to CO2? What is the sensitivity of productivity to climate, to CO2? All these kinds of things. So, I think there. It's I don't know. It's kind of like that. All good models look the same, and all bad models are bad for different reasons, right? Or unhappy. I think there's not going to be one story, right? And there's going to be, as we look into it, there's going to be like 10 different questions. Is there a fire-driven dieback of the Amazon? Is there what happens in the boreal? Is there how fast is the the leading edge of the boreal forest expansion move? How fast does the trailing edge, recede, et cetera, et cetera? There's going to be all these different questions, and we're going to need to then come up with answers to every single one of them.
Can I follow?
So that's easy then.
Charlie, as I mentioned, the structure is important to understand the ecological and biological and biogeochemical processes. But into predictions, projections, everything, all the process you mentioned, everything down to influence the productivity and residence time. And I understand that our conclusion could upset quite some people, and certainly stunned some people. And but all those fire, permafrost, the multi-layer translocations, transport, all basically eventually all those processes influence the carbon trajectory through their influence on the residence time and the carbon input.
All right, can I actually respond to that? I agree, Yichi, but just as a thought experiment, like the structural difference of, say, adding permafrost carbon versus adding an extra pool that has a very long turnover time. Both of those will have the effect of increasing the turnover time of carbon, right? So in that sense, mathematically they might be equivalent, except for the fact that if you just add a really low turnover time, you haven't changed the sensitivity of turnover time to temperature. Whereas if you've made the structural change of adding permafrost carbon, you've changed the sensitivity of turnover time to temperature. And so in that sense, they're not equivalent, right? And so what I'm saying, it's the sensitivities that really matter. I'll stop now.
Yeah, Charlie and I quite often don't agree, so probably we should discuss offline. Yeah.
Adriana, did you want to make a point?
Yeah, I guess I was just wondering if, Charlie or Ichi, if there is a way to parse out. So I know, with Ichi, you're finding that it's like the turnover time and the carbon input, but can you diagnose which processes are contributing to that difference? So for, what Charlie was saying with fire and permafrost, can you kind of somehow, without running and modifying the models a ton, turn on and off those processes to see, where it's coming from?
With a matrix approach, yes. And, we have published quite a few papers to demonstrate. And let's say we compare two models, and if two model differs, and we can identify exactly what caused them, and actually we can, identify down to the particular parameter on the line of code, and how the two model and why they differs, and how much, how those differs caused by what process and what parameters. Because we developed the so-called traceability analysis, and we can trace down the individual parameters and the individual model structures. Yeah. Well, again, we only provide a framework to understand, to diagnose uncertainties. But as Charlie mentioned, permafrost, the sensitivity, the fire is supposed to be that strong or that frequency. Our framework only can tell you whether fire in the particular region, the different way of incorporate the fire among the different model, how much uncertainty cost. But what's the realism of a fire in a particular region still depends on data, observations. So we are happy to work with you guys if if you're interested in. I understand it's some of our conclusions are stunning and probably upsetting. Yeah.
Other questions for either any of the speakers? I guess I was looking back I was like, man, what was the first talk? It was only an hour ago. But, both Isla and Lucas talked about temperature variability, and then these last two talks are more on carbon cycle variability. So like very different timescales, very different processes, but kind of fundamental, I guess in some ways, some similarities. Yeah, and I guess Dave, just thinking about your question about how are land models and ocean models so different, it seems like nowhere in the tuning process of CLM were we thinking about daily temperature variations in the model, and nowhere in the kind of parameterization of CLM were we thinking about even 2100 time horizons for predictions. It's like we're doing our best to create a model that looks realistic now, and then kind of flying blind in the future, both at like the long time scales, so 2100 or 2300, and the short time scales in terms of diel variation or daily variation in temperature. I don't have a solution.
Can I say something about the ocean and the land?
Sure.
And I'm kind of a Norway. I probably only understand a little bit about land, but I know almost nothing about the ocean. But probably about 5 years ago, I was leading a manuscript, try to understand why ocean and the land carbon cycle, their predictability are so different. And certainly this manuscript, still in my computer and didn't finish. But at that time, I talked with quite many people, including Matthew Long and Scott Donnie, and so my understanding well, we have kind of a manuscript in the quite, probably 60% of shape. And what I learned during that process was that in terms of predictability, the land process, the longer the process are, and the less predictable. So for example, fire regime in a region that's defined the frequency, those actually very, the predictability is quite low. But the ocean carbon cycle, it's a contrast. Those longer the process are, actually predictability is very high. And the shorter those process, the predictability is lower. And the land carbon cycle is just the opposite. So that's why, because ocean carbon is, again, I'm no expert. It's only based on the experience, unfinished manuscript. And the ocean carbon cycle, the longer process, it's highly predictable. And that's why this long-term, the patterns are much more consistent in the for ocean than land. That's probably one day I should get to the manuscript published, but.
I'm used to you telling us that we should have read a manuscript that you already have written, not one that you haven't written yet, EG. Charlie, go ahead.
Well, yeah, I guess I was just to maybe go full circle to Dave's talk. I was wondering, and this is why I'm so excited about the PPE, right? Because obviously CLM5 is an incomplete representation of the terrestrial system. It doesn't have dynamic vegetation. It doesn't have a lot of things. But what it does have, we can actually start to systematically explore. And I think it's, this whole question of, the structural, the fact that the CMIP models are a weird mixture of both structural and parametric differences makes them really difficult to interpret, even if you apply each of these approaches, because you don't know how much of it's just a single line of code versus how much of it's an emergent change because of, a different way of thinking about a process. Whereas, if we can start to look at, the sensitivity of transient, projection X to parameter Y, and then start to really focus on it, I think it's going to be really powerful. So I'm really excited and excited to move away from looking at CMIP and towards large PPEs of single models so we can start to answer some of these questions.
Here, +1 now. Would be a nice change. Keith, Lindsay, go ahead.
Yeah, I think I concur with that. I think the PPE stuff is really exciting. I do just want to make one more comment on the apparent lack of spread in the ocean results. If you look at other processes in the ocean where there's a stronger role of biology, like oxygen deoxygenation issues or oxygen minimum zones or change in primary productivity, there's not quite the agreement in the CMIP models that there is for ocean carbon uptake. So I think this is something you alluded to, Dave. I think the ocean carbon uptake is primarily, to first order, solubility and circulation, ventilation. And the role of biology plays a lesser role for that particular metric. Whereas, so I think there's greater consensus amongst the models on that, or general patterns. The details there's divergence. But for processes where you get or metrics that are more fundamentally driven by biogeochemistry, I think you see more divergence. And you can see that in intercomparison papers that look at different stressors of ocean ecology and how the different CMIP models do diverge for projections on those metrics.
Julie has a comment in the chat about, is there any comment on the advantage or disadvantage of PPE over the multi-model simulations?
I can start. I mean, they're just so different, really. The multi-model simulations, let's just presume we're not dealing with climate forcing uncertainty. So maybe instead of land-only simulations, all forced with the same climate. They're assessing all the structural differences. It's just kind of uncontrolled. So in the PPE, we're not considering structural differences across the models that exist. So those are obviously important too, critically important, and we're not planning to assess that, although we could extend the PPE to assess, the structural features we have in our model where we can make changes. But that's the main thing. So I don't know if it's an advantage or disadvantage, except in the sense of the advantage of the PPE is that this one of the first times we've done this for parameters. The structural uncertainty has been assessed imperfectly many times in multi-model comparisons. That'd be my answer. I'm sure others have different subtleties to their perspective.
I mean, I guess maybe to add to that, I think it'll be interesting is, hopefully other modeling centers follow suit and do PPEs on their models, and then we can look at, what is the structural, what is the difference of sensitivity of parameter Y based on the structure, and combine the both aspects. Eventually, because you don't want to just rely on any one model, but even if CLM5 is really great.
Katie put something in the chat. I was thinking the same thing. Like, what do you call an ensemble of parameter perturbation ensembles? Not sure. Abby, go ahead.
Yeah, I was just going to ask, do we know of any other groups that are planning something similar? I know there's the ones from the previous versions of the UK model. Are there any plans to update that? Is anybody aware of other efforts in other groups?
Hopefully after the CLM5 PPE is a resounding success, everybody else will want to do it too.
I totally agree. It'd be really exciting to be able to see that across multiple models.
Yeah, for Lucky, it follows a similar pattern to the large ensemble. Right, that now there are large ensemble MIPS. Although I think that's an easier ask than the PPE enforcement. It doesn't really it's easy to run your model multiple times if you have a computer that can handle it. PPE requires more underlying infrastructure, unfortunately.
Great. Well, it's 2:30, so maybe to avoid Zoom fatigue, so we can all come back fresh and ready for more talks tomorrow at 9. I'll suggest we adjourn for the day. It's a good time to, I don't know, go have coffee or something else by yourself. It's very sad.